Tonight, I want to begin with something very small, almost just a social courtesy. Perhaps you're listening from an apartment in the middle of a city, from a quiet village, from somewhere near the sea, or from a very distant corner of the earth. If you enjoy science that is slow, gentle, and deep enough to both soothe the mind and expand your understanding, you can leave a like, subscribe to the channel, and tell me where you are right now. In a story about distance and connection, that detail feels strangely fitting, because that is really where our question begins: distance. Imagine two particles born together and then gradually drifting away from one another. One moves to the left, the other to the right. They may end up separated by a few meters, a few kilometers, or even entire continents. By ordinary intuition, any connection between them should fade with distance. But at the quantum level, what happens is far more unsettling to that intuition. When one particle is measured, the other reveals a correlation that seems to appear instantly. There is no signal we can see traveling across the gap, no invisible tether in the classical sense, no familiar mechanism that explains why two things so far apart still remain so perfectly in step with each other. This is not a metaphor, it is not poetry, nor is it wild speculation. It is a phenomenon in quantum mechanics known as quantum entanglement. What makes it even harder to dismiss is that it does not exist only on paper. From optical laboratory benches in Europe to satellites flying high around the Earth, scientists have tested this phenomenon under very different conditions. And the more they test it, the clearer the picture becomes. Nature truly does allow this kind of correlation to exist. Very early on, Erwin Schrödinger recognized that this was not some minor detail of quantum theory. In the 1930s, he introduced the word entanglement and regarded it as the defining feature of the entire theory. Einstein reacted in the opposite way. He became famous for the phrase spooky action at a distance, because to him, physics ought to describe a world made of separate parts, each with its own properties and influenced only by events nearby. This is where the clash of ideas becomes profound. In the classical picture, objects exist as independent entities. Each object has its own position, its own velocity, its own mass. If something changes, there must be some nearby cause producing that change. Planets orbit stars. Solid bodies move through space. Cannonballs follow curved trajectories through the air. All of it reinforces the feeling that the universe is built from things that are separate from one another. For most of the history of science, that was almost a foundational assumption. But quantum mechanics opens the door to another possibility. Under certain conditions, two systems can no longer be described as two independent entities. They share a single mathematical state. Even when widely separated in space, their physical description remains interwoven. And so the seemingly obvious assumption that each thing possesses its own separate reality, isolated from everything else unless something actually travels between them, suddenly becomes far less secure. From John Bell's work in the 1960s onward, and through decades of increasingly refined experiments, carefully designed tests have kept pointing in the same direction. Nature does not behave according to local hidden variable theories. The correlations we observe go beyond what classical realism would allow, yet that does not mean any useful signal is racing faster than light. There is no violation of the universe's speed limit. Relativity still stands firm, so whatever is happening must be much subtler than that. Perhaps what we call separation is not as fundamental as we once believed. Perhaps connection does not necessarily arise because one thing sends a message to another, but from a deeper shared structure, a common origin embedded in the mathematical description of reality itself. And that is the path we will follow tonight. From the classical assumption of separateness to the way quantum theory redefines the very concept of a physical state. From the debate between Einstein and Schrödinger to Bell's theorem and the experiments that followed, and then further still into modern ideas about information, entropy, the geometry of spacetime, and even the possibility that the very fabric of space may emerge from patterns of entanglement. There will be no sensationalism here, no mysticism dressed up as science, only slow, careful steps through ideas that are strange precisely because they are real. So wherever you are listening from right now, perhaps thousands of kilometers away from another listener, hold on to one very quiet thought. Distance may no longer mean exactly what it once did, and connection may run deeper than the empty space between things. If we look at the world through the lens of classical physics, everything appears to follow an order that feels very easy to accept. An object changes because something acts upon it. A push, a pull, a collision, or a cause transmitted through some force. Nothing naturally happens out of nowhere, at a distant place. For a change to occur, there must be an influence. For there to be an influence, there must be a path that can be traced. From this emerges a foundational assumption that classical physics almost treats as self-evident: separability. Each physical system possesses its own state. What happens here is determined by what is present here, together with any influence arriving from outside through a continuous process that can be described and traced. In that view, the world is assembled from separate parts. Newton was the one who first gave this intuition a precise mathematical form. In the 17th century, his laws of motion showed how forces change motion, while the law of universal gravitation described how masses attract one another across space. It is true that gravity appears to act at a distance, yet even within Newton's picture, each object still retains its identity as a distinct entity. The Earth does not lose its individuality simply because the sun pulls on it. At every moment, it still has its own definite position, its own definite momentum, and a state evolving in its own way. Then, in the 19th century, Maxwell changed how we tell that story, though he did not break its core spirit. He unified electricity and magnetism in a theory of fields, replacing the idea of mysterious action at a distance with a far more continuous picture: the electromagnetic field filling space. A charge does not jump its influence directly to a distant place. Instead, it acts locally on the field, and disturbances in that field spread outward like waves at a finite speed. Those waves, it turns out, are light. Maxwell's equations showed that electromagnetic disturbances propagate at a fixed speed of about 300,000 kilometers per second. Later measurements refined that number with extraordinary precision. But the important thing is not only the value itself. What matters more is the principle behind it. Physical influence does not leap instantaneously from one place to another. It propagates through space in a continuous way. Einstein later elevated that principle to the level of a fundamental law of nature. In 1905, in the theory of special relativity, the speed of light in a vacuum was no longer merely a result of electromagnetism. It became the ultimate limit for every signal, every piece of information, every causal influence. Nothing can travel faster than light without colliding with the very structure of spacetime itself. If two events are separated in such a way that light cannot travel from one to the other in time, then during that interval no physical cause can connect them. This idea is called locality. In this context, it has a very clear meaning. Physical influences must be mediated by nearby interactions, and every signal is constrained by the geometry of spacetime. This is not some philosophical luxury. It lies deep in the foundations of modern physics. Particle accelerators operate according to it. Satellite communications depend on it. Even the global positioning system relies on it to such a degree that without relativistic corrections, GPS would quickly lose accuracy at the level of meters. So by the beginning of the 20th century, physics seemed to stand firmly on two pillars. The first was separability. Systems possess their own properties that can be defined independently of distant systems. The second was locality. All influences propagate through continuous physical processes and never exceed the speed of light. Perhaps the reason these two principles took such deep root is that they fit so naturally with everyday experience. If you place two coins at opposite ends of a table, flipping one will not determine the outcome of the other. If they somehow always matched each other, we would assume a hidden connection between them. And even if glue held them together, that glue would still represent a local link. Our intuition has been shaped by experiences like these. Philosophers of physics have not overlooked this foundation. Howard Stein, for example, analyzed separability as a basic principle of classical field theories. In such theories, the state of a complex system is completely determined by the states of its individual parts and the spatial relations between them. There is no need to add some hidden global structure beyond what has already been specified locally. The whole, in this sense, is nothing more than the sum of its parts. And perhaps that is the most important thing to feel at this point in the story. This is not merely a way of doing physics. It is also a way of experiencing the world. A chair remains a chair, whether someone sits on it or not. The moon does not borrow its identity from Mars. Each object exists as itself, and interactions occur when forces act between them. Even gravity, though it stretches across astronomical distances, can ultimately be described through a local field, or later through the geometric curvature of spacetime in the theory of general relativity that Einstein introduced in 1915. From the perspective of general relativity, the world appears remarkably coherent. Mass and energy curve spacetime precisely where they are present, and objects move according to that curvature. There is no need to imagine invisible threads stretching between distant celestial bodies. Spacetime itself provides a continuous stage for all motion. While causal influence still respects the limit set by the speed of light, the picture is elegant, internally consistent, and strongly supported by experiment. From familiar phenomena like falling objects to the motion of entire galaxies. That is precisely why the shift introduced by quantum mechanics at the beginning of the 20th century was so striking. When Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger gradually shaped this new theory, what emerged was not simply a few unusual formulas. It was an entirely different way of describing reality. In the mathematics of quantum mechanics, there exist composite systems whose total state cannot be written as the separate states of their parts simply combined together. Two particles can become bound within a single shared wave function, and that description resists every attempt to split them into two independent accounts. This point is essential to keep clear. What we are dealing with is not merely correlation in the familiar classical sense. It is not the case of two things that were predetermined and later simply reveal what had already been arranged. Here, their properties only truly acquire meaning in relation to one another. In other words, what begins to tremble is not only our explanation of signals or the speed at which information travels. What is being questioned is the assumption that physical systems can always be treated as separate parts. Imagine two particles created together in a carefully prepared experiment. According to quantum theory, their shared state can contain correlations so strong that measuring one particle immediately restricts the possible outcomes of the other. The distance between them might be a few kilometers. It might span an entire continent. Yet at the moment the measurement occurs, no pulse of signal is detected racing across the space between them. No secret flash moves from one side to the other. If you look at each measurement individually, everything still appears random. Only when the results are compared afterward does the structure of correlation reveal itself. So the real question is not, how did information travel? The deeper question is far more subtle. How can such correlated behavior persist across space without the familiar form of interaction? In classical physics, we usually handle correlations like this by tracing them back to a common cause. Two clocks set at the same time may remain synchronized for a while. Two gloves placed beforehand into separate boxes allow us to infer that if one box contains the left glove, the other must contain the right. But in examples like these, the properties were determined in advance. Quantum entanglement refuses to fit neatly into that explanation. Measurement outcomes cannot be understood as having been predetermined by local hidden variables, at least not in any way that both preserves locality and agrees with experimental evidence. Later, in the 1960s, John Bell would sharpen this tension into a precise mathematical statement. Yet, even before Bell's work, the unease was already present. What quantum theory introduced was not only randomness. It introduced a new kind of description in which the state of a composite system cannot always be separated into independent states of its parts. It is the mathematics of superposition and tensor products that opens this door. It allows combinations that cannot be cut cleanly into separate components in the way classical physics assumes. For that reason, entanglement should not first be understood as a puzzle about something traveling from one place to another. Rather, it is a challenge about structure. The mystery lies not in something moving from one particle to the other, but in why the formal description of the pair refuses to split cleanly into two independent descriptions. In classical mechanics, if you know the state of system A and the state of system B, then the state of the combined system is simply those two placed side by side. There is no deeper layer of information. But in quantum mechanics, that simplicity dissolves. The joint state can contain a kind of relational information that cannot be completely reduced to the individual subsystems. The whole, in this case, is not merely the sum of its pieces. None of this means that relativity is overturned. The speed limit of light remains intact. The no-signaling principle still firmly holds. This phenomenon cannot be used to transmit controllable information faster than light. Yet even though the speed limit is never crossed, the conceptual foundation of the world begins to shift. The idea that reality is built entirely from independent parts starts to lose some of its certainty. The familiar image of isolated objects, each carrying its own well-defined properties, becomes softer and less absolute. And what replaces it is neither chaos nor mysticism. It is a more intricate architecture of reality, where relationships sometimes precede individual components, and where the whole can carry more structure than the sum of its parts. From this quiet shift, quantum entanglement emerges not as a bizarre exception, but as a natural consequence of how quantum mechanics describes the world. The stage is now set. Within its own domain, classical separability and locality remain extremely reliable. Yet deep inside the quantum framework, another pattern has begun to form, quietly inviting us to reconsider how things separated by vast distances may still remain connected in a deeper sense. There was a moment in the history of science when it truly seemed that the physical picture of the world was almost complete. Motion had classical mechanics, heat had thermodynamics, electricity, magnetism, and light had all been unified by Maxwell within a powerful theoretical framework. From the outside, the remaining work appeared to be little more than smoothing out small irregularities on an otherwise finished structure, minor technical problems waiting to be resolved. But sometimes those small wrinkles open the door to profound change. One of them was black-body radiation, the light emitted by hot objects. Experiments showed that energy was not distributed arbitrarily across frequencies. Instead, it followed a very specific law. And here, classical physics began to stumble. If one applied the principle of equal energy distribution, classical theory was forced to predict that at higher and higher frequencies, energy would accumulate without limit. Later, this absurd prediction came to be known as the ultraviolet catastrophe. But nature did not behave that way at all. In 1900, Max Planck proposed a fix that even he initially did not regard as a deep statement about the nature of the world. He simply tried a bold assumption. Energy is not exchanged continuously between matter and radiation, but in discrete packets. Each unit of exchange is proportional to the frequency, with an extremely small constant standing in between what would later bear his name. The Planck constant is so tiny that in everyday life we never notice its effects. Yet in the microscopic world, it sits quietly behind almost every physical process. At the time, Planck's proposal resembled a mathematical trick designed to rescue experimental data. But just 5 years later, Einstein took that same idea and pushed it much further. In his 1905 explanation of the photoelectric effect, light was no longer merely a wave in the familiar sense. It began to behave as though it were composed of individual quanta units we now call photons. And one detail here is crucial. The energy of each photon is determined not by the intensity of the light, but by its frequency. Increasing intensity means more photons, not photons carrying more energy. That was the moment when the foundations began to shift. Energy no longer appeared as a continuous flow that could be divided indefinitely. Nature began to reveal a structure more discrete than we had imagined. What started as a patch for a theoretical gap gradually became a clue that the microscopic world might be built very differently from classical intuition. By the 1920s, quantum mechanics was no longer just a collection of scattered ideas. It began to crystallize into a clear mathematical form. In 1925, Werner Heisenberg introduced matrix mechanics. A year later, Erwin Schrödinger developed wave mechanics. At first glance, these two approaches looked quite different. One relied on arrays of numbers and algebraic relations, while the other resembled the language of continuous waves. Yet it was eventually shown that they were mathematically equivalent. Among the names often mentioned in this story, Pascual Jordan is sometimes pushed into the background, even though his role was significant. He helped formalize the procedures of quantization and opened the path toward what would later develop into quantum field theory. In particular, Jordan clarified how classical quantities could be elevated into operators' mathematical objects that no longer obey the familiar commutative multiplication of classical mechanics. One of the most important signs of this shift is the canonical commutation relation between position and momentum. Expressed in words, it says that if you multiply position by momentum and subtract momentum multiplied by position, the result is the imaginary unit times Planck's constant divided by 2 pi. Nothing like this exists in classical mechanics. This non-commutativity is not merely a technical detail. It embeds Heisenberg's uncertainty principle directly into the structure of the theory. Then John von Neumann arrived and placed this entire collection of ideas onto a more rigorous mathematical foundation. In 1932, he presented quantum mechanics within the framework of Hilbert space, an abstract vector space equipped with an inner product. It may sound dry, but this is where the real conceptual shift becomes visible. A physical system is no longer described as a list of predetermined properties such as a specific position or velocity. Instead, it is described by a state vector in Hilbert space. Observable quantities, such as position or spin, are represented by self-adjoint operators acting on that vector. This means that the quantum state does not directly tell us where an object really is or how it moves in the classical sense. Rather, it encodes the measurable possibilities more precisely, the probabilities of different measurement outcomes. And once we accept that the state is a vector, superposition appears almost inevitably. If one state is allowed to exist and another state is allowed to exist, then any linear combination of them is also a valid state. This is perhaps one of the points where classical intuition begins to lose its footing most clearly. Consider a particle whose spin is about to be measured along some axis. In classical thinking, the particle must already possess one definite orientation or the other. But in quantum mechanics, its state may be a superposition of both possibilities. And what the state vector carries are not simple classical probabilities, but complex probability amplitudes. From this point onward, the language of physics begins to move away from the familiar world of definite properties and into a deeper structure, stranger, perhaps, but also more precise. What remained missing to turn the abstract language of quantum amplitudes into something that could be compared with experiments was a bridge. Max Born provided that bridge. The rule that bears his name states something simple but foundational. To find the probability of a result, we do not take the amplitude directly, but the square of its magnitude. In other words, probability equals the amplitude multiplied by its complex conjugate. The formula may sound modest, but it has survived countless experimental tests from electron diffraction to atomic spectroscopy, and it continues to hold firm. Yet the truly strange aspect is not that amplitudes produce probabilities. The strange part is that amplitudes can interfere. If a result can be reached by two different paths, quantum mechanics does not ask us to calculate the probability of each path and then add them, as classical intuition would suggest. Instead, the amplitudes are added first. Only afterward do we square the result to obtain the probability. It is precisely this ordering that produces interference patterns, one of the most distinctive signatures of the quantum world. The double-slit experiment makes this nearly impossible to miss. Even when particles are fired one at a time, individually, the traces they leave gradually accumulate into a pattern that resembles a wave. At that moment, the idea that a particle always carries a definite trajectory begins to lose its certainty. Between measurements, the quantum state does not tell a story about a clear path through space. Instead, it retains a structured set of possibilities, each weighted by a probability amplitude. When we move from a single system to multiple systems together, the shift goes even further. Classical physics is very economical in this respect. The state of a composite system is simply the states of its parts placed side by side. If system A has state A and system B has state B, then the combined system is just A and B. No deeper layer of description sits between them. But within the Hilbert space framework, composite systems are built from the tensor product of the individual spaces. And that mathematical structure opens a new possibility. There exist states that cannot be written as a simple product of two independent vectors. Such states are precisely what we call entangled states. They carry a kind of relational information that cannot be reduced to the properties of each individual part. Here, the structural revolution of quantum mechanics becomes unmistakable. The state of the entire system may contain correlations that cannot be explained by assigning independent local properties to each subsystem and then simply combining them. It is no surprise that philosophers of science have paid particular attention to this point. James Ladyman, among others, has taken it as a serious indication for a position known as structural realism. From that perspective, what science captures most reliably is not the hidden essence of individual objects, but the network of relations and mathematical structures connecting them. The most enduring content of a theory lies not in telling us what a thing really is, in some simple ontological sense, but in how precisely it describes patterns of relationships. Quantum mechanics seems to lean strongly in that direction. The state vector does not describe tiny billiard balls carrying hidden labels inside them. Instead, it describes a network of possible measurement outcomes and the relations between them. Once systems fall into an entangled state, that relational aspect becomes central to the entire description. This does not mean that objects disappear from the picture. It simply means that their properties do not always exist as completely separate entities. In von Neumann's formalism, this is written quite plainly. The state of a composite system is a single vector within a larger Hilbert space. If that vector cannot be separated into individual vectors for each subsystem, then the systems are said to be entangled. The mathematics does not treat this as a strange phenomenon appearing only in rare circumstances. On the contrary, it treats it as a natural and often very common possibility. In fact, the situation goes even further. If two quantum systems interact through any non-trivial coupling, their joint state will usually become inseparable. Maintaining complete independence between them actually requires special conditions. In that sense, what classical intuition, once treated as the default separability, becomes the exception in the quantum world. This represents a deep reversal. In the classical picture, we assume systems are independent until a force acts upon them. But in quantum mechanics, interaction often leaves behind a relational structure that persists even after the systems have separated in space. The shift brought by quantum theory, therefore, does not lie only in discreteness or in the uncertainty principle. It lies in the very way we organize physical description. The quantum state is not constructed to record fixed, intrinsic properties locked inside each object. It is built to encode possibilities and relationships. Superposition reflects the linear structure of Hilbert space. Born's rule converts amplitudes into testable probabilities, and the tensor product opens the possibility that a composite system may possess a structure that cannot be separated into independent parts. From that point onward, the picture of reality begins to change in a way that can no longer return to the old classical intuition. One thing must be held firmly from the very beginning. Nothing here forces relativity to collapse. The speed of light still stands as a causal limit. Within standard quantum mechanics, no equation allows us to control a signal in a way that would cross that boundary. There is no hidden doorway through which information can race faster than light. Yet even though that limit remains intact, something else has changed. We can no longer simply assume that systems far apart always possess independence in the classical sense. This shift is not loud. It does not feel like an explosion that shatters all previous physics. It is quieter than that, and perhaps for that reason even deeper. It does not break the wall in front of us. It moves the ground beneath it. The familiar picture of a universe built from separate blocks that only occasionally touch and interact gradually gives way to something different. Relationships are not late additions, but are woven into the mathematical structure of the theory from the very beginning. In that light, the complete separability assumed by classical physics no longer looks like a universal truth. It appears instead as an extraordinarily effective approximation, one that works beautifully at large scales, but may not be the ultimate foundation. Within that refined structure, entanglement emerges as a natural consequence, not as something bizarre inserted from outside, but as a direct expression of how quantum states are constructed. In 1935, Erwin Schrödinger wrote his famous paper in response to the challenge raised by Einstein, Podolsky, and Rosen. He did not view the issue as a minor technical puzzle. Instead, he recognized in it the deepest disturbance within the entire theory, and he gave it a name: entanglement. For Schrödinger, this was not an accidental side effect. He regarded it as the defining feature of quantum mechanics, the point where the theory departs most dramatically from classical lines of thought. In other words, if we want to touch the truly distinctive part of quantum physics, we should not begin with vague slogans about strangeness. We should look exactly where Schrödinger pointed: the structure of states in composite systems. Each quantum system is represented by a state vector in Hilbert space. When two systems are combined, we do not simply place their descriptions side by side as classical intuition would suggest. Their joint description lives in the tensor product of their individual Hilbert spaces, and it is precisely this mathematical structure that allows states to exist which cannot be written as the simple product of a state for the first system multiplied by a state for the second system. If the joint state can be written in that way, the systems are separable. Each retains its own independent description. But if such a decomposition is impossible, then the systems are entangled. This is important because it is a completely precise and entirely structural definition. It does not require talking about signals. It does not yet require discussing measurement. It does not even require mentioning distance. It asks only one question: can the mathematical form of the joint state be factorized or not? If it cannot, then the correlations contained in the global description cannot be reduced to the idea that each part simply carries its own independent local properties. Schrödinger saw the consequence clearly. Once two systems interact and enter an entangled state, their gradual separation in space does not automatically restore their independence. Distance does not cause the tensor product to factorize itself into independent pieces. Space may expand between the systems, but the joint state can still preserve its inseparable structure. This was the context in which the EPR paper appeared almost simultaneously. Einstein, Podolsky, and Rosen did not write that paper to celebrate quantum mechanics. Their goal was to argue that the quantum description of the time was incomplete. They considered a pair of particles that had once interacted and then separated. In their reasoning, an experimenter could choose to measure one quantity on the first particle and thereby infer with certainty the value of the corresponding quantity for the second. If the first measurement revealed position, the position of the second particle could be deduced. If instead momentum were measured, then the momentum of the second particle could be predicted. From this, Einstein and his colleagues proposed a criterion for physical reality. They argued that if one can predict with certainty the value of a quantity without disturbing the system, then there must exist an element of reality corresponding to that quantity. Based on this principle, they concluded that the second particle must possess definite values for both position and momentum, even though quantum mechanics does not allow both to be assigned simultaneously in its formal description. Therefore, they argued, the quantum theory must be missing something. There must exist hidden variables carrying those true values. What troubled Einstein most, if we look closely, was not simply the presence of probability or randomness. His deepest concern lay with separability and locality. He believed that two systems far apart in space must possess their own real states, independent of one another. That was the foundational intuition he was unwilling to abandon. And it is precisely here that the confrontation between classical thinking and quantum structure reveals its full depth. What troubled Einstein was not simply that quantum mechanics used probabilities. In his correspondence with Max Born, he returned again and again to the same concern. The real state of one system should not depend on what someone chooses to do with another system far away. For him, this was not a minor detail. It marked the boundary between a world in which things retain their individual reality and one in which distance no longer seems to protect independence. At one point in the 1940s, Einstein referred to such correlations as spooky action at a distance. He did not mean this in any mystical sense. He was trying to express the unease that the quantum formalism seemed to allow a kind of instantaneous connection across space, something that conflicted with his relativistic intuition about space-time. For Einstein, if two systems were separated in space, what happened to one should not touch the reality of the other. There is an important point here that is often misunderstood. Einstein's objection is frequently reduced to the idea that he simply disliked randomness. But the issue is more subtle. Determinism is the idea that the present uniquely determines the future. Classical mechanics works that way. Given the initial state and the forces involved, the future trajectory can be calculated. Realism in the EPR debate, however, is something different. It is the belief that physical systems possess definite properties that exist independently of whether we observe them. One could accept a fundamentally probabilistic world and still maintain that behind those probabilities lies an underlying reality. So Einstein's deepest discomfort was not directed merely at uncertainty. He could accept probabilistic laws if they still rested on real states beneath them. What he found harder to accept was the possibility that quantum mechanics blurred the independent reality of distant systems themselves. That was the point where the principle of separability, something he deeply trusted, seemed to be under threat. Schrödinger looked at the same issue but followed a different path. He did not rush to conclude that it revealed a flaw in the theory. Instead, he accepted that entanglement was something that had to be faced as a core feature. Once two systems interact, he realized, their joint state will often become entangled, and that condition does not simply disappear when they later move far apart. The mathematical description continues to treat them as part of a single entity. Consider the familiar example involving spin. Imagine two particles prepared so that the total spin of the pair is zero. If one particle is measured and found to have spin up along some axis, the other will show spin down along that same axis. Yet before the measurement, quantum mechanics does not assign a definite value to either particle individually. What it assigns is a shared state containing perfect anticorrelation. This is where classical thinking begins to falter. We cannot describe this situation as if the first particle already carried a hidden label up and the second carried a hidden label down, simply waiting to be revealed. The quantum description is not built that way. The correlation is not something added afterward, it is embedded directly in the structure of the state vector itself. The entire description is holistic from the beginning. When one of the particles is measured, the joint state is updated according to the rules of quantum mechanics. Locally, the outcome appears completely random. You cannot control it. But when it is later compared with the measurement performed on the distant particle, the correlation appears with perfect consistency. The reason is not that a hidden signal managed to race across space at the right moment. The reason is that the pair never possessed separate descriptions in the first place. The distance between them may grow, but the shared state does not automatically split into two independent parts. Schrödinger sensed this very clearly. Entanglement challenges the classical intuition of individuality. In familiar physics, Two objects that are far apart are simply two objects. But in quantum mechanics, they can still inhabit a single inseparable state, and that inseparability is not an extra patch added to the theory. It arises directly from two foundational elements of the formalism: the linear structure of Hilbert space and the tensor product used to combine systems. Once you accept superposition for individual systems and use the tensor product to describe composite ones, entanglement is no longer a rare possibility. It becomes a mathematical inevitability. To eliminate it, one would have to rewrite the entire framework of the theory. In that sense, entanglement does not sit at the edges of quantum mechanics. It lies at the very center of its architecture. Moreover, any interaction that couples two systems can generate entanglement. In fact, at microscopic scales, systems are almost always entangled with their surrounding environment. Decades later, the theory of decoherence developed by H. Dieter and Wojciech Zurek would show that this widespread entanglement is precisely what gives rise to the seemingly definite appearance of the classical world at larger scales. But in 1935, those implications were only beginning to emerge. So the disagreement between Einstein and Schrödinger was never about the experimental data. It was about how to interpret the structure of the world itself. Einstein looked at entanglement and saw evidence that the theory must be incomplete, perhaps requiring hidden variables to restore independent reality to distant systems. Schrödinger looked at the same phenomenon and saw the opposite possibility. Perhaps the world itself is not built upon classical separability after all. The question therefore became sharply defined. Is the mathematical formalism of quantum mechanics merely an incomplete description of a deeper reality that remains local and separable, or is it revealing that separability itself is not fundamental? Decades later, John Bell would push this question toward a more decisive answer. But even before Bell, the seeds of that conclusion were already present in Schrödinger's recognition of the central role of entanglement. It was not a flaw in the theory, nor an experimental anomaly. It was a structural property of the quantum state itself. The crucial point is this: once two systems have interacted, what remains is not necessarily just two separate pieces sitting side by side. They may enter a shared description, and that description can resist being split back into independent parts. Spatial distance does not automatically dismantle that structure. What classical intuition has long assumed, that the whole is nothing more than the sum of its parts, may turn out to be merely a very effective approximation at the scales of everyday life. At the quantum level, the relations encoded in a joint state can sometimes be more fundamental than the individual properties of each part. Once we begin to see things that way, the question, how can two distant things remain connected, starts to change its nature. It is no longer about whether some hidden signal might be traveling across the empty space between them. Instead, it becomes a deeper question. How does nature organize its most fundamental descriptions? For several decades after the EPR paper, the debate surrounding entanglement remained largely philosophical. Einstein hoped that deeper hidden variables might exist, capable of restoring a separable and local description of reality. Schrödinger, by contrast, accepted that entanglement might be fundamental. Yet at that time, there was still no clear experimental path capable of deciding between those two perspectives. The turning point arrived in 1964. John Bell, working at CERN, published a short paper that completely reshaped the landscape of the debate. What was remarkable about Bell's approach was that he did not try to explain entanglement with a new intuitive picture. Instead, he did something far sharper. He asked, if the world truly obeys both locality and realism in the EPR sense, what observable constraints must follow from those assumptions? Together, those assumptions form what is now called local realism. Locality means that an event occurring here cannot instantaneously influence an event far away. Realism means that physical properties must possess definite values even before a measurement takes place. Bell proved that any theory attempting to preserve both assumptions must obey certain statistical inequalities. In short, They impose an upper bound on the strength of correlations that can appear between measurements performed on systems separated in space. This is what makes Bell's theorem especially powerful. It does not target one specific hidden variable model. It does not claim that one particular version fails while another might succeed. Instead, it makes a broader statement. All local hidden variable theories must satisfy the same statistical constraints. If experiments produce results that exceed those limits, then it is not just a single model that fails. The entire class of such models runs into trouble. In modern presentations, the story is often told using two observers named Alice and Bob, positioned far apart from one another. Each measures one particle from an entangled pair, and each has the freedom to choose between different measurement settings. If the world obeys local realism, then Alice's result can depend only on Alice's measurement setting and on shared hidden variables carried by the particles since their creation. The same must hold for Bob. From these assumptions, Bell showed that the combined correlations among many measurements must remain within a specific limit. Quantum mechanics, however, predicts something different. It allows correlations that are stronger than what local realism permits. And this prediction concerns statistics, not a single event. No individual measurement by itself proves anything. The crucial point lies in the pattern that emerges after many measurements are compared. In 1969, John Clauser, Michael Horn, Abner Shimony, and Richard Holt reformulated Bell's theorem into a version that was easier to test experimentally. This form became known as the CHSH inequality. Its importance lies in making the problem more concrete. It identifies a specific combination of correlations that experimenters can directly measure and compare against a theoretical limit. Within the framework of local realism, the magnitude of this combination cannot exceed 2. That number is not arbitrary. It follows directly from the algebra of predetermined outcomes, each assumed to lie between 1 and +1. If the world behaves according to such a model, the value 2 is a strict ceiling. But quantum mechanics predicts that under the right conditions, the same quantity can reach, which is approximately 2.828. The gap between 2 and 2.828 is enough to transform the debate from a philosophical argument into an experimental question. For the first time, the issue that once hung between Einstein and Schrödinger could be tested directly. Does nature truly obey a reality that is both local and separable? Or is its deepest structure different from what classical intuition once promised? When John Bell's theorem opened the door to experimental testing, a new question immediately appeared. If quantum mechanics truly allows correlations stronger than classical physics, why can't that strength increase without limit? The answer lies in a very special boundary. The largest value quantum theory permits in this class of problems is called the Tserilson's bound, named after Boris Tserilson, who derived it in 1980. This is a subtle point. Quantum theory surpasses the classical threshold of 2, but it does not leap all the way to the absolute maximum that pure mathematics could imagine. In other words, quantum mechanics produces stronger correlations than classical physics, but not arbitrarily strong ones. The very structure of Hilbert space constrains it within a specific limit. That shows that entanglement is not a lawless explosion of correlations. It is tightly restricted by the mathematical architecture of the theory itself. And this is precisely what makes the story even more elegant. Nature does not merely reject the classical picture, it also rejects even more extreme non-local possibilities that mathematics alone would allow. Indeed, one can imagine hypothetical models that generate correlations stronger than quantum ones, while still obeying the no-signaling principle. These theoretical constructs are often called Popescu-Rorlich box. If such objects existed in nature, they could push the same correlation expression to the algebraic maximum value of 4, while still respecting the rule that no information travels faster than light. Yet nature does not go that far. Experiments consistently approach the Tserilson limit but never exceed it. Quantum mechanics, therefore, appears as a remarkably precise middle ground. It goes beyond classical local realism, yet it avoids the extreme non-locality that abstract logic might allow. Then, in 1982, Arthur Fine sharpened the picture even further. His theorem states that the possibility of constructing a joint probability distribution for all possible measurement outcomes is mathematically equivalent to the requirement that Bell inequality conditions be satisfied. This may sound technical, but the implication is powerful. If one assumes that every measurement outcome already possesses a predetermined value even for measurements that are not actually performed, then Bell-type inequalities must hold. If experiments violate them, such a consistent assignment of predetermined values cannot exist. This clarifies something that might otherwise be underestimated. Violating Bell inequalities is not a small statistical deviation, nor a technical artifact. It means that no local hidden variable model can reproduce the correlations we actually observe. The debate therefore reaches a clear crossroads. Either the concept of locality must be relaxed in some way, or the EPR notion of realism must be revised, or we must accept that both cannot be maintained simultaneously. At this point, however, extreme care is necessary. Abandoning locality in this context does not mean accepting faster-than-light communication. John Bell himself was very clear about this. Within quantum mechanics, the no-signaling principle remains intact. One cannot use measurement outcomes in one location to send controllable information faster than light to another. At the operational level, the causal structure of special relativity remains preserved. The tension appears only when we attempt to tell a deeper story about what is truly happening beneath the measurement outcomes. If we insist that physical properties exist independently of observation, then those properties cannot be purely local features confined within isolated regions of space. The observed correlations force any underlying model to contain some form of non-local dependence. Alternatively, one can take another path and reconsider the very concept of reality itself. Certain interpretations, such as relational quantum mechanics or cubism, do precisely that. In these views, measurement outcomes are not revelations of pre-existing local properties but instead relational events or observer-dependent updates of knowledge. Perhaps the most remarkable aspect of Bell's work is that he pulled a debate that once belonged almost entirely to philosophy and placed it directly onto the laboratory table. After that point, the question was no longer simply what we prefer to believe about the world, but rather what numbers nature actually produces. Those numbers have now been measured repeatedly over many decades, beginning with the famous experiments of Alain Aspect in the early 1980s, and continuing with increasingly sophisticated tests across Europe, North America, and Asia. Researchers have consistently observed violations of Bell inequalities under conditions designed to eliminate alternative explanations. And here the numbers truly matter. In well-designed experiments using entangled photons, the measured correlation values often reach around 2.7 or higher, very close to the quantum maximum of about 2.828. Meanwhile, every classical local hidden variable model remains capped at 2. That gap is not merely a matter of a few digits. It is an experimental signature showing that the world does not sit on the side of classical intuition. It stands somewhere else where the structure of relationships runs deeper than the old idea that reality is built from fully independent parts. At this stage, what is striking is no longer that Bell inequality violations occurred once or twice. What matters is that they have appeared repeatedly across many laboratories, using different technologies over several decades. This is not a statistical anomaly that disappears when experiments are repeated more carefully. The numbers keep returning, persistently, as if nature is repeating the same answer again and again. Yet that answer is not unlimited. Even though quantum theory surpasses the classical boundary, it does not go arbitrarily far. There is a very clear upper ceiling known as Tsirelson's bound. The mathematical structure of Hilbert space, together with Max Born's probability rule, prevents quantum correlations from increasing without bound. This is an important signal. Quantum mechanics does not simply break the old rules chaotically. It crosses the classical boundary, yet still operates within a tightly ordered internal structure. In other words, if classical physics draws one boundary for correlations, Quantum theory not only steps beyond it but also establishes a new boundary of its own. Beyond that, in purely theoretical thought experiments, one can imagine superquantum models producing even stronger correlations. But nature does not choose that extreme. Instead, it sits precisely in a middle region, stronger than classical correlations, but weaker than the logical extremes mathematics could permit. This restraint suggests that quantum theory forms a coherent framework with its own geometry and architecture, not a random violation of older principles. From this point, John Bell's theorem leaves two clear conclusions. First, the world does not obey local realism in the sense hoped for by Albert Einstein, Boris Podolsky, and Nathan Rosen in the EPR paradox. Second, the non-classical correlations nature displays are not arbitrary. They possess shape, limits, and structure. Entanglement, therefore, is not a chaotic breakdown of the old order. It is a departure from classical separability, but a disciplined one, guided by the mathematical framework of quantum mechanics itself. At this moment, a question that once seemed philosophical moved decisively into the realm of experiment. It was no longer merely about how we prefer to interpret the world. Now there were quantitative predictions. Classical models required Bell inequalities to hold, while quantum mechanics predicted their violation by a specific amount. The debate had shifted from speculation to laboratory challenge. By the late 1970s, the theory was largely ready. The difficulty lay in the real world: imperfect detectors, signals traveling through cables, and the stubborn complexity of nature compared with clean theoretical models. In that context, the early 1980s experiments conducted by Alain Aspect and his team at the Institut d'Optique near Paris became a historic milestone. They produced entangled photon pairs through cascade decay processes in excited calcium atoms. When such an atom decays in two steps, it emits two photons whose polarizations are correlated exactly as quantum mechanics predicts. What made the 1982 experiment special was not merely the production of these photon pairs, but the way Aspect's team addressed the locality issue. They rapidly switched measurement settings while the photons were already in flight. In other words, the measurement orientation on one side could change faster than light could travel between the two detectors. This design directly targeted what later became known as the locality loophole. If measurement choices are made quickly and independently, no slower-than-light signal can secretly coordinate results between the two sides. Aspect's results matched the predictions of quantum mechanics. The CHSH inequality was violated, and the measured correlations exceeded the classical limit of 2 while approaching the quantum value. Of course, those experiments did not immediately close every possible escape route for alternative explanations, but they achieved something crucial. They made the defense of strict local realism far more difficult. As experimental technology improved, each advance narrowed the safe territory for classical interpretations. During the 1990s and early 2000s, Anton Zeilinger and his collaborators in Vienna pushed photon entanglement experiments much further. Instead of atomic cascades, they used spontaneous, parametric down conversion in nonlinear crystals to generate entangled photon pairs with higher efficiency and better control. In this process, a single high-energy photon entering a crystal splits into two lower-energy photons whose polarizations become entangled. Importantly, these photons did not remain confined to small optical tables inside carefully shielded laboratories. Zeilinger's group distributed entanglement across kilometers of optical fiber and even transmitted entangled photons through open air between islands in the Canary Islands. These experiments demonstrated that entanglement is not a fragile phenomenon. Existing only under idealized conditions, it can persist across significant distances in real environments. Still, even as tests became stronger, two major concerns continued to haunt Bell experiments. One was the locality loophole, partly addressed by rapidly changing measurement settings. The other was the detection loophole. In many early experiments, only a fraction of emitted photons were actually detected. If the detected subset was not representative of the entire ensemble, hidden variable models could exploit that sampling bias. For that reason, truly closing the detection loophole requires experiments with extremely high detection efficiency. To truly close the detection loophole, experimental physicists eventually realized they could not simply repeat the same photon experiments and hope for better luck. Either photon detectors had to become dramatically more efficient, or entirely different physical systems had to be used, systems whose states could be measured with much higher reliability. This necessity led to a major milestone in 2015, when Ronald Hansen and his team at Delft University of Technology reported what many consider the first loophole-free test of the Bell inequality. Instead of photons, as in many earlier experiments, they worked with electron spins in diamond, specifically defects known as nitrogen vacancy centers inside the crystal lattice. These solid-state systems offered a clear advantage: much higher detection efficiency, while still allowing measurement stations to be placed far apart. In the Delft experiment, the two stations were separated by more than a kilometer, and the crucial events, the choice of measurement settings and the recording of results, were arranged so that they were space-like, separated in spacetime. Put simply, no signal traveling at or below the speed of light could move from one station to the other in time to coordinate the outcomes. That is why this experiment is often described as a turning point. It simultaneously addressed the two major issues that had long complicated Bell tests: the locality loophole and the detection loophole. And even under these carefully controlled conditions, the results did not drift back toward classical intuition. The observed correlations continued to violate Bell inequalities with clear statistical significance, exactly as predicted by quantum mechanics. Delft did not remain alone for long. Around the same time, other groups reached similar conclusions through very different experimental paths. In the United States, researchers at the National Institute of Standards and Technology used entangled photons, combined with highly efficient superconducting detectors, to close the detection loophole. In Austria, other teams focused on ensuring that measurement choices were made randomly and timed precisely to maintain strict locality conditions. Different physical systems, different instruments, different laboratories, yet the final answer consistently came out the same. And that answer had a very distinctive shape. The correlations always exceeded the classical limit, but they never surpassed the quantum boundary known as Tsirelson's bound. This is what makes the story especially compelling. If the data fluctuated wildly, sometimes higher, sometimes lower, we might suspect technical noise. But that is not what happens. Nature does not merely reject local hidden variable models. It rejects them with remarkable precision, producing correlations exactly within the range predicted by quantum theory. It is worth pausing to understand what closing loopholes really means. It is not simply fixing a mathematical mistake or correcting a programming error. In this context, a loophole is an opening that still allows an alternative explanation, one that remains compatible with both the experimental data and a classical hidden variable model. If detectors miss too many events, one could argue the observed sample is biased. If measurement choices are made too slowly or are somehow correlated, one could claim information had time to pass between the stations before the measurements were completed. Closing loopholes means designing experiments so that such explanations no longer survive under reasonable physical assumptions. Of course, from a purely logical standpoint, one can always imagine even more exotic possibilities. One example is superdeterminism, where hidden variables would have predetermined not only the outcomes, but even the experimental settings themselves. But rescuing classical realism in this way comes at a steep cost. It requires abandoning extremely basic assumptions about statistical independence and experimental freedom. For that reason, in practical scientific terms, the experimental community now regards the violation of Bell inequalities as a firmly established empirical fact. Entanglement has also been tested over distances far beyond laboratory tables. In 2017, the Chinese satellite Messius, part of a program led by Jian Weipan, distributed entangled photons between ground stations separated by more than 1,000 kilometers. This was no longer the scale of an optical bench or a city cable network. It was a distance comparable to the width of a small country. Yet even across such scales, the same correlation pattern remained intact. Across this entire chain of experiments, one calm pattern keeps repeating. When measurement settings are chosen independently and detection efficiency is high enough, the observed correlations consistently match the predictions of quantum mechanics. They exceed the classical boundary, yet never surpass the quantum limit. If we look simply at the numbers, the story becomes remarkably stable. The CHSH parameter rises above 2, often reaching around 2, 7 or slightly higher, depending on the experimental conditions. When the apparatus works properly, it does not obediently fall back into the classical region. This is not a fragile anomaly. It is a robust property of the world. Bell's theorem is elegant because of its conceptual clarity, and the experiments are powerful because of their consistency. Together, they tell us that entanglement is no longer merely a philosophical curiosity. It is an experimentally confirmed feature of nature. Systems that are far apart, if prepared in certain shared quantum states, will display correlations that no local hidden variable model can reproduce. At this point, however, listeners often begin to feel uneasy. If results at distant locations match each other more strongly than classical models allow, does that mean something is truly racing through space faster than light? Has special relativity quietly been set aside? The answer is no, and this is where another result of modern quantum theory becomes crucial: the no communication theorem. This theorem states clearly, in precise mathematical terms, that quantum mechanics does not allow controllable information to travel faster than light, even when systems are entangled. This is not a patch added to rescue relativity, nor a philosophical reassurance. It follows directly from the structure of quantum states and from Max Born's probability rule. Returning to the familiar picture of two observers far apart, each measuring one particle of an entangled pair, the joint state of the pair indeed contains correlations. Those correlations appear clearly when the observers later compare their results. But there is a crucial detail. Locally, the statistics observed by each side do not change depending on the measurement choice made at the other location. No matter which measurement is chosen here, the probability distribution seen there remains exactly the same. In other words, the local outcomes remain random, and that is precisely why entanglement cannot serve as a faster-than-light communication channel. Entanglement produces correlations, but it does not produce outcomes that can be controlled in order to send messages. At this point, quantum mechanics manages to preserve two ideas that seem difficult to hold together. It allows correlations beyond classical physics, yet it does not violate the causal speed limit imposed by relativity. If someone on one side tried to use entanglement to send a message by switching back and forth between different measurement settings, the observer on the distant side would receive nothing at all. The pattern of results seen locally would remain exactly the same. Only after the two observers later gather their data and compare them through ordinary communication do the correlations become visible, and that ordinary channel still cannot travel faster than light. The reason is not that nature simply forbids it as an after-the-fact rule. It follows directly from the mathematics of quantum theory. When two systems are described by a joint density matrix, the predictions for one subsystem are obtained by taking the partial trace over the other. The result is a reduced density matrix, which determines all local measurement probabilities. Crucially, the reduced state on one side does not depend on which measurement is chosen on the other side. In formula language, the probability of an outcome on side B is computed from the trace of B's reduced density matrix multiplied by B's measurement operator. That reduced matrix contains no record of the distant observer's choice of measurement. This independence follows from the linear structure of quantum mechanics. If it were otherwise, the consequences would be dramatic. One could change a measurement setting and instantly transmit a binary signal across arbitrary distances, collapsing the framework of relativity. But that does not happen. When Albert Einstein introduced special relativity in 1905, he built it upon two clear principles. The laws of physics are the same in all inertial frames, and the speed of light in vacuum is invariant and serves as the universal speed limit. Over more than a century, this structure has been tested in countless ways, from particle accelerators to satellite timing systems. Even everyday technology such as GPS would lose meter-level accuracy if relativistic corrections were ignored. Quantum mechanics does not break that structure. It coexists with it. For that reason, when physicists say quantum correlations are non-local, the phrase must be understood carefully. If it is interpreted as some faster-than-light causal signal racing across space, the meaning becomes distorted. What John Bell's theorem shows is not that signals exceed the speed of light, but that no local hidden variable model can reproduce the correlations we observe. Correlation is not the same thing as transmitted influence. In classical physics, correlations often arise from a common cause in the past. If two objects are prepared together and later separated, their agreement simply reflects that shared origin. Quantum mechanics also involves a kind of shared origin, but it is not just a set of hidden labels assigned in advance. Instead, the interaction prepares a shared entangled state, and that state itself encodes the correlations. When measurements are performed later, the correlations are revealed, but the measurement on one side does not send a controllable influence to the other. The no communication theorem protects precisely this point. It guarantees that quantum mechanics cannot be used to transmit information faster than light, preserving relativistic causality. This compatibility is not accidental. In quantum field theory, where quantum mechanics and relativity are unified, locality is preserved through the commutation relations of field operators. Observables associated with space-like separated regions commute with one another. Put simply, if light cannot travel between two regions during the relevant time interval, a measurement in one region cannot disturb the measurement in the other. That commutativity is one of the structural features ensuring the theory remains consistent with relativity. What remains remarkable is that even while causality is protected in this way, quantum correlations still exceed the limits allowed by classical physics. They surpass the value of 2 inches, the CHSH inequality, and within quantum theory they can approach about 2.828, the Tsirelson's bound. The universe therefore seems to sit on a very delicate boundary. On one side lies classical local realism with weaker correlations. On the other side lie hypothetical, super-quantum models, producing even stronger correlations without signaling. Quantum mechanics sits precisely in between, strong enough to break classical separability, yet disciplined enough to preserve relativistic causality. This balance is what makes entanglement so profound. It is not a chaotic loophole in the laws of physics. It is a structured feature emerging from the geometry of Hilbert space and from the probability rule introduced by Max Born. One may loosely imagine entanglement as a connection stretching across space, but that image can mislead. More precisely, it is a property of the joint state created when systems interact. The connection does not travel anywhere. It does not propagate or move through space. It simply exists within the mathematical structure of that shared state. When measurements occur, the joint probabilities reflect this encoded structure. That is why outcomes at distant locations can align in ways that no local hidden variable model can explain. Yet this alignment cannot be turned into a superluminal communication channel. No one can control their local outcome well enough to send a deliberate message. Quantum mechanics therefore modifies our understanding of locality without destroying relativity. What disappears is not causality itself, but the assumption that distant systems always carry fully independent properties beneath the surface. What remains intact is the independence of local statistics. The distinction between these two layers is subtle but crucial. Relativity governs what can cause influence and transmit information. Quantum entanglement governs how the joint probabilities of outcomes are organized across space. The two frameworks stand side by side without contradiction. Once this becomes clear, the deeper significance of entanglement begins to shift. Its importance does not lie in breaking the speed limit of nature. It lies elsewhere, in how physical properties are defined, in the role of measurement context, and in the realization that outcomes cannot always be understood by examining isolated parts alone. What emerges is not a technology for faster-than-light messaging, but a transformation in the structure of physical description itself, where correlations arise from inseparable states and where the questions we ask of nature become part of the answers we obtain. The fact that entanglement cannot be used to send signals faster than light closes one dramatic possibility, but at the same time it opens an even more intriguing door. If two distant systems cannot communicate instantaneously, yet still cannot be described as completely independent parts, then perhaps what needs revision is not only our intuition about distance, but also our intuition about physical properties themselves. From this point, the question becomes sharper, not merely whether the world is truly local, but whether properties exist as pre-existing values independent of the context in which they are measured. Entanglement already shakes the idea that distant systems can always be described separately. But contextuality goes even further. It does not require two particles at opposite ends of space. Instead, it raises a question about a single system. Can we say that this system carries definite values for each observable, regardless of the measurement context we choose? In 1967, Simon Cochin and Ernst Specker transformed this question into a theorem that sharpened the foundations of quantum mechanics. If Bell attacked the combination of locality and realism, the Cochin-Specker theorem targets a different assumption: non-contextual realism. This idea states that a physical quantity possesses its own value, and that this value does not depend on which other compatible quantities are measured alongside it. In classical physics, this seems almost too obvious to mention. The mass of a book does not change simply because we decide to measure its temperature or width at the same time. We are used to thinking that properties belong to objects, and measurement merely reveals them. Quantum mechanics does not allow this intuition to go all the way. In Hilbert spaces of dimension 3 or greater, the Cochin-Specker theorem shows that it is impossible to assign definite pre-existing values to all quantum observables, while simultaneously preserving two conditions. First, the assigned values must respect the mathematical relations among observables. Second, they must be completely independent of the measurement context. This may sound technical, but the core idea is clear. If we imagine that every observable already has a definite value, and that this value does not care about what other measurements accompany it, the structure of the theory itself leads us into contradiction. The reason lies in the fact that quantum observables do not stand alone like isolated squares on a board. There exist sets of compatible quantities, meaning they can be measured together, yet the same observable can appear in many different compatible sets. If one tries to assign it a single fixed value that keeps all overlapping sets consistent simultaneously, eventually the structure collides with itself. In simpler terms, the value of a quantum observable cannot always be treated as an intrinsic label attached to the system, regardless of the measurement circumstances. Context becomes part of the story. This point must be clearly separated from non-locality. Non-locality concerns correlations between distant systems, exactly the phenomenon highlighted by Bell. Contextuality, by contrast, can arise within a single system and does not require spatial separation at all. It does not ask how two distant locations are connected. Instead, it asks how strongly a measurement outcome depends on the overall structure of the measurement being performed. A particularly elegant way to sense this boundary comes from a toy model introduced by Robert Speckens in 2007. The model is deliberately simple. It keeps a classical structure at the underlying level, but imposes a limit on the observer's knowledge. This limitation alone produces behaviors that look strikingly quantum, including certain forms of interference and constraints that resemble epistemic restrictions. The model demonstrates that a lack of information can mimic many features of the quantum world, but it cannot go all the way. Speckens' model remains non-contextual, and for that reason it cannot reproduce the full range of contextuality exhibited by quantum mechanics. This failure tells us something important. Contextuality is not merely an effect of limited knowledge. It does not simply say that we know too little about the system. Rather, it says that within the structure of observables themselves, in the way they relate to one another inside Hilbert space, there exists a genuinely non-classical feature that a non-contextual model cannot preserve. For a more concrete picture, consider a spin, one system. Measurements of spin along different directions are not independent quantities unrelated to each other. They correspond to operators bound together by strict mathematical relations. The Kochen-Specker theorem shows that it is impossible to assign predetermined spin values along every direction while respecting these relations, unless one allows the value to depend on the set of measurements performed alongside it. In other words, unlike classical intuition, quantum observables need not carry values independent of context. Thus, the challenge to classical realism does not end with the strange behavior of distant particles that appear to remain linked. Even without entanglement, even when considering a single particle alone, the picture of intrinsic properties values that exist in advance and remain completely independent of measurement begins to crack. Contextuality pushes the quantum revolution deeper into the very concept of property. What makes this even more fascinating is that contextuality is no longer viewed solely as a foundational curiosity. In recent years, it has also been recognized as a resource. In certain models of quantum computation, especially measurement-based quantum computing, specific forms of contextuality appear to enable tasks that classical models struggle to perform. Theoretical work, including that of Robert Rausendorf, has connected contextuality with the computational power of quantum systems, and in some frameworks even suggests that contextuality is a necessary ingredient for universal quantum computation. Perhaps the most intuitive way to see this is the following. Classical logic works comfortably in a world where bits obey clear truth tables, where values can be assigned consistently in advance. But in the quantum world, where observables are bound by contextual relations, the patterns of allowed correlations no longer fit neatly inside that framework. They reflect a richer, subtler logical structure, one that is far harder to simulate with non-contextual hidden variable models. And there, contextuality emerges not merely as a strange feature of quantum mechanics, but as one of the deepest signs that nature is not written in the classical language we once assumed to be universal. Contextuality by itself is not a guaranteed ticket to every quantum computational advantage. Yet the more closely it is examined, the more it appears to be one of the key non-classical ingredients that separates quantum information processing from classical computation. For that reason, it is difficult to dismiss it as merely an elegant but useless philosophical curiosity. It is a structural feature of the theory, and that structure leaves very concrete consequences in how we understand and how we harness the quantum world. What matters is that the departure from classical thinking does not arise only when two systems are pulled far apart in space. Even on a single laboratory bench with a trapped ion or a superconducting qubit, contextuality is already present. It does not require astronomical distances or particles flying in opposite directions. It emerges directly from the algebra of observables. The classical worldview assumes that properties already exist, independent of whether we measure them and independent of one another. Quantum mechanics replaces that picture with one in which measurement outcomes are tied to the overall structure of the experimental arrangement. This does not mean that measurement invents reality out of nothing. That phrasing is too strong and ultimately misleading. A more accurate statement is that quantum mechanics suggests the properties revealed are relational within a specific context. The Kochen-Specker theorem makes this precise. It is not about faster-than-light signaling or mysterious influences across space. It states that we cannot assign to every quantum observable a set of pre-existing values within a single global scheme, while ignoring the measurement context. Placed alongside Bell's theorem, the picture becomes even sharper. Bell shows that classical models with local hidden properties cannot explain correlations between distant systems. The Kochen-Specker theorem shows that even within the local domain, properties themselves refuse to fit neatly into that classical assignment of values. Entanglement tells us that distant systems may still share a structure that cannot be separated. Contextuality tells us that even when we look at a single system, its properties do not always exist as independent labels waiting to be read out. At that point, the shift becomes clearer. The classical image of a world made of properties that exist independently, merely waiting to be revealed, begins to give way to a far more subtle picture. Observables no longer stand alone, they live within a network of compatible measurements. The outcome depends not only on the system being interrogated, but also on the structure of the question itself. Yet there is no collapse into vagueness here. No supernatural mystery intrudes. The mathematical framework of Hilbert space, operator algebra, and the Born rule keeps the entire structure in a consistent order. In other words, quantum mechanics does not abolish order. It replaces classical independence with structured relational constraints. Within that quiet substitution, the meaning of measurement itself changes. It is no longer simply the act of lifting a lid to reveal a property that was already sitting inside the object. It becomes part of the structural network through which outcomes are determined. The deeper one looks, the clearer it becomes that the classical ideal of intrinsic, non-contextual properties is not the bedrock of the quantum world. What endures instead are the relations encoded in the formalism, together with the probabilistic rules that connect them to experiment. From this point, an almost unavoidable question emerges. If entanglement and contextuality are such fundamental features, why does the everyday world look so strongly classical? The table remains exactly where it is. Planets follow stable orbits. The cup on the table does not appear to be simultaneously here and somewhere else. Objects seem to possess definite positions, clear separations, and stable measurement outcomes. If the deepest level of theory denies properties independent of context, why does the surface of reality look almost entirely the opposite? The bridge between these two sides began to take shape in the 1970s through the work of H. Dieter Ziehe. He introduced what is now known as the theory of decoherence. Ziehe's idea appears simple, yet its consequences are profound. In reality, no system is perfectly isolated. Every system interacts with its surrounding environment, however weakly. Those weak but continuous interactions reshape how quantum superpositions manifest at the level we can observe. In the mathematics of quantum mechanics, a particle can exist in a superposition of two different positions. If the system were perfectly isolated, that superposition would continue evolving under the Schrödinger equation without ever turning into a definite outcome by itself. But the real world does not grant such isolation. A dust particle drifting through air is anything but quiet. Every second, it collides with countless air molecules. Ambient light scatters off it. Thermal radiation continually exchanges energy with it. With every such interaction, the dust particle becomes a little more entangled with its environment. Ziehe realized that when a system becomes entangled with an enormous number of environmental degrees of freedom, the different components of a superposition can no longer interfere with each other in any practically accessible way. Coherence between the branches does not vanish in a metaphysical sense, but it becomes dispersed into correlations with the environment so vast that, for the system alone, the interference terms effectively cease to play an observable role. The system still has a complete quantum description, but if we look only at its reduced description after tracing out the environment, the density matrix becomes nearly diagonal in some basis. In more everyday language, macroscopically distinct states simply stop interfering with one another in any effective way. That is decoherence. Later, Wojciech Zurek developed the idea further with the concept of environmentally induced decoherence. Zurek emphasized that the environment does not merely destroy coherence randomly. It also tends to favor certain states that remain more stable under the environment's continuous monitoring. He called them pointer states. These are states of the system that either become minimally entangled with the environment or maintain the most stable correlations with it. For a macroscopic object such as a dust particle, those pointer states correspond almost exactly to well-defined positions in space. This provides a deep reason for the familiar intuition that objects always appear to be in one place. It is not because quantum mechanics ceases to apply at the macroscopic scale. Rather, the environment constantly selects stable position states so effectively that all other possibilities are suppressed almost instantly in practical observation. The everyday world looks local and definite not because it is non-quantum, but because its quantum nature is continuously sculpted by the environment into a classical appearance. What is truly astonishing is the timescale on which this process occurs. For a dust particle roughly a micrometer in diameter floating in air at room temperature, if two possible positions differ by only a tiny fraction of a micrometer, decoherence between them can occur on the order of 10 to the power of -20 seconds. That is so fast that, on the scale of human experience, the macroscopic world has almost no opportunity to appear as a naked quantum superposition. And precisely there, the classical appearance of everyday life emerges not as the opposite of quantum mechanics, but as a consequence of quantum systems constantly interacting with their environment. A timescale on the order of 10 to the power of -20 seconds lies almost completely beyond ordinary intuition. Written out, it is a decimal point followed by 19 zeros before reaching the first meaningful digit. On the scale of human experience, that is effectively instantaneous. And it is precisely this astonishing speed that helps explain why the macroscopic world appears so stable, even though its foundation remains quantum mechanical. What matters here is that no superluminal collapse mechanism is being secretly added. The Schrödinger equation continues to govern the entire combined system of object plus environment. Decoherence theory does not rewrite the rules, nor does it patch the theory with some new intervention. The heavy lifting is still done by entanglement. The object does not stand alone. It rapidly becomes correlated with countless degrees of freedom in its surrounding environment. The difficulty is that no one, not even an observer, can access that entire enormous entangled state. The observer is also a physical system embedded within the same world, and so what they can reach is only a tiny fragment of the global state. As a result, the reduced description available to them takes on an effectively classical appearance. What we call everyday reality begins to emerge from that very limitation of access. Zurek pushed this idea further with a framework he called quantum Darwinism. The name sounds metaphorical, but its aim is quite precise. The central idea is that certain states of a system leave traces of themselves redundantly in the environment. Information about those states does not appear just once. It is copied into many independent fragments of the environment. As a result, different observers can access the same kind of information without ever directly touching the system itself. Think of a tree standing in a forest. Light scatters off its surface in every direction. Photons carry information about the tree's position and shape to countless observers. Each observer intercepts only a tiny fraction of that photon stream. Yet the remarkable thing is that they all still agree on where the tree is. In the picture of quantum Darwinism, the environment acts like a broadcasting channel for information about the preferred states, the pointer states selected by decoherence. It is this redundancy that creates the sense of objectivity. If information about a system was stored in only one fragile environmental degree of freedom, stable agreement among many observers would be impossible. But when that information is copied over and over again throughout the environment, stability and consensus begin to emerge. In that way, classical reality is not the absolute bedrock. It is something that emerges from the way quantum entanglement between system and environment is organized and dispersed. This also helps clarify why two distant macroscopic objects appear independent. Their environments, in practice, monitor them almost separately. Decoherence suppresses interference between macroscopically distinct states so quickly that such superpositions do not survive long enough to leave observable effects. In the reduced description accessible to observers, each object appears as if it carries its own definite properties. Even if the underlying global state of the universe remains deeply entangled, the local states we actually encounter are approximately classical. Seen this way, the original tension surrounding separability is put into its proper place. Classical style independence is not written directly into the fundamental equations. It appears only in regimes where decoherence has rendered interference between branches negligible. It is an emergent pattern, not a basic axiom. Even so, one must be careful. Decoherence does not by itself answer every interpretational question. It explains why outcomes appear stable, why we do not observe macroscopic superpositions, and why interference disappears from ordinary life. But it does not, in every interpretation of the theory, by itself select which outcome is actually realized in a single measurement. That is why different interpretations still have room to stand. Many worlds uses decoherence one way. Objective collapse theories use it another way. The power of decoherence lies not only in philosophy, but also in experiment. In quantum optics and mesoscopic physics, its effects have been directly observed. Interference fringes disappear when a system is allowed to interact with an uncontrolled environment, and they reappear when isolation is improved. This is not idle speculation. It is something laboratories have seen. Superconducting qubits in quantum computing experiments provide a very clear example. They must be shielded with extraordinary care from environmental noise, because even a small amount of unwanted entanglement with the environment quickly degrades coherent quantum behavior. Depending on the design, decoherence times in such systems may last only from microseconds to milliseconds. Engineers therefore pour enormous effort into extending those tiny intervals by even a little. That effort is living evidence that the predictions of Z and Zurek are not merely blackboard abstractions. When the environment steals away phase information and disperses it into degrees of freedom that are practically inaccessible, interference becomes almost impossible to observe. The deeper lesson is this: entanglement is not rare, it is everywhere. Everything interacts. Everything becomes correlated with its surrounding environment. The difference between the microscopic and the macroscopic does not lie in one having entanglement while the other does not. The difference lies in the consequences of entanglement. On small scales, we can still isolate systems well enough for superpositions to maintain coherence. On large scales, entanglement with the environment grows so rapidly that classical behavior overwhelms almost everything else. For that reason, classical reality, with its separate objects and definite positions, is not the rival of quantum mechanics. It is an approximation that emerges in regimes where decoherence has suppressed interference. Independence is not a principle carved into the deepest layer of physics. It is a stable pattern generated by the interaction between quantum systems and their environments. The world looks classical not because quantum mechanics fails, but because entanglement with the environment works with overwhelming efficiency. Seen in that light, entanglement no longer sits at the margins of physics as some strange exception. It becomes the very mechanism that helps make our everyday world stable and predictable. The independence of the objects around us is real in the practical sense. It is just not the most fundamental thing in principle. And once one accepts that entanglement is experimentally real and structurally central, a natural question arises: what, in the end, does that say about the ontology of the world? The equations are clear. The predictions work. Bell inequalities are violated. Decoherence explains why the world looks classical. But the question of what truly exists remains open. It is here that the major interpretations of quantum mechanics begin to diverge. The Copenhagen interpretation, usually associated with Bohr and Heisenberg, is the most famous of these viewpoints. In this framework, the quantum state is not regarded as a direct copy of objective reality in the way a classical state might be. Instead, it encodes the possibilities of measurement outcomes. Bohr emphasized complementarity. Some experimental arrangements reveal wave-like behavior, others reveal particle-like behavior, and no single description can fully capture both at once. The meaning of physical quantities is therefore tied to the measurement context. From the Copenhagen point of view, entanglement shows that we cannot always assign independent states to quantum systems prior to measurement. When two particles are entangled, the shared state describes the correlations that may appear. When a measurement takes place, one outcome becomes actualized, and the formalism is updated accordingly. The so-called collapse of the wave function is, in this way of thinking, usually not taken as a physical signal shooting through space, but rather as a change in the description or in our knowledge of the system. The entire formalism is used as a tool for predicting the probabilities of outcomes recorded by classical measuring devices. Many find that restraint appealing, but many others find it unsatisfying. That dissatisfaction is precisely why Hugh Everett, in 1957, proposed a radically different path. In his many worlds interpretation, there is no collapse at all. The Schrödinger equation is not exempted during measurement. It governs every physical process without exception. When a measurement is performed on an entangled system, the combined state of system plus measuring device does not jump into a single possibility. Instead, it evolves into a superposition of different branches. In one branch, the device records spin up. In another, it records spin down. And in Everett's picture, both branches continue to exist within the universal wave function of the universe. In the many worlds interpretation, entanglement is no longer a problem that must be solved and then set aside. It becomes the very engine of branching. A measurement does not end with the world selecting a single outcome and erasing the remaining possibilities. Instead, the system, the measuring device, and ultimately the observer are all drawn into a larger entangled state, where each possible result corresponds to a different branch of the global state. No collapse occurs, no hidden variables are added. The price of this dynamical cleanliness is a far more expansive ontology. Reality becomes a vast branching structure of decohering worlds. Within this framework, decoherence plays an almost essential role. It explains why branches effectively cease to interfere with one another, and why from inside a branch an observer experiences only one outcome as having occurred. David Wallace and other modern proponents have gone further, attempting to derive the Born rule within this collapse-free picture, using arguments inspired by decision theory. Many worlds thus preserves locality at the level of the Schrödinger equation, but it radically changes what we mean by a single result. Entanglement becomes universal and never erased. What appears as independence is merely the emergent effect of decoherence between branches. David Bohm, beginning in 1952, pursued a path that was almost the opposite in intuition. He sought to restore particles with genuinely definite positions. In Bohmian mechanics, sometimes called pilot wave theory, particles always occupy precise locations. The wave function still exists and still evolves according to the Schrödinger equation, but rather than being the whole story, it also guides the motion of particles through what Bohm called the quantum potential. The guidance equation can be expressed in words by saying that the velocity of a particle is determined by Planck's constant, divided by its mass, multiplied by the imaginary part of the gradient of the wave function divided by the wave function itself. Through this rule, if the initial particle positions are distributed according to the Born rule, all the familiar predictions of quantum mechanics are recovered, but the price in this case appears elsewhere. In Bohmian mechanics, entanglement does not disappear. It manifests as a non-local form of guidance. The wave function of a composite system does not live in ordinary three-dimensional space, but in the configuration space of the entire system. As a result, the motion of one particle can depend instantaneously on the configuration of another particle far away, through that shared wave function. Basil Hiley and others have continued developing this framework, extending it even toward quantum field theory and information theoretic perspectives. Bohmian mechanics preserves realism in a stronger sense than Copenhagen or Cubism, because particles genuinely possess definite positions. Yet to achieve this, it must give up locality at the fundamental level. Even so, the theory is constructed in such a way that it still forbids faster-than-light signaling at the level of observable phenomena. Another viewpoint, more recent and philosophically quite different, is Cubism. In this perspective, Christopher Fuchs and collaborators do not treat the quantum state as a description of objective reality existing independently of the observer. Instead, they interpret it as representing an agent's degrees of belief about the future experiences that the agent themselves may encounter. In Cubism, Probability is personal and Bayesian. The Born rule is no longer a statement about how the world really is, but rather a normative rule guiding how an agent should update expectations when considering possible actions and experiences. From this angle, entanglement is no longer a mysterious physical thread stretching across space. It becomes a way of encoding an agent's expectations about correlations among experiences that may arise from different measurements. Cubism does not deny the existence of an external world, but it shifts the focus of quantum mechanics toward the relationship between the agent and that world. The wave function is not out there as a physical object existing independently in space. It resides in the probabilistic bookkeeping of the agent. This viewpoint avoids the ontological expansion of many worlds and also avoids the non-local hidden variables of Bohmian mechanics, but in return, it draws quantum mechanics closer to experience and information than to objects and mechanisms. What is remarkable is that despite these deep philosophical differences, all these interpretations meet at exactly the same experimental ground. They all accept the Born rule. They all agree that Bell inequalities are violated. They all accept decoherence and its consequences. To this day, no known experiment can decisively determine which interpretation is correct. The differences lie not in what laboratory instruments will record, but in what we say exists behind those numbers. Copenhagen emphasizes measurement and the role of classical description. Many worlds embraces a universally entangled and branching universe. Bohmian mechanics restores definite trajectories but accepts fundamental non-locality. Cubism transforms the wave function into a personalized tool for managing expectations. Yet there is one point none of them can deny. Entanglement is real within the structure of the theory. No interpretation is free to treat it as an optional accessory. Each must explain why composite systems are described by states that cannot be factorized, and why nature violates Bell inequalities. In that sense, entanglement is experimentally settled yet conceptually open. It anchors the theory firmly to data, while leaving space for philosophy. And perhaps it is precisely in that quiet gap between equation and meaning that the deepest layers of quantum mechanics continue to unfold. Up to this point, entanglement has often been told in the language of particles: two photons from a common source, two spins in a singlet state, two systems that interact and then separate. But modern physics does not regard particles as the ultimate layer of reality. Beneath those familiar images lies a deeper framework: quantum field theory. In this picture, the fundamental ingredients of nature are not tiny particles drifting through space, but fields extending throughout space-time. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Quarks appear as excitations of quark fields. Even what appears to be empty space is not empty in any simple sense. It is filled with quantum fields. Seen from this perspective, entanglement is no longer something added after two particles collide. It is already embedded within the structure of the fields themselves. One particularly rigorous way to express this is through algebraic quantum field theory, a framework that Rudolf Haag played a central role in developing during the 1950s and 1960s. Instead of placing particle states at the center, this approach assigns to each region of spacetime an algebra of observables. Each region possesses operators corresponding to quantities that can be measured within that region, and these local algebras are required to satisfy very precise mathematical properties, including locality. Observables belonging to space-like separated regions must commute with one another, preserving the spirit of relativity. The surprising fact is that even in the vacuum state, the lowest energy state, where no particles are present in the usual sense, there is still entanglement between different regions of space. This idea is deeply counterintuitive, because in everyday language, vacuum sounds synonymous with emptiness. Yet in quantum field theory, the vacuum is not a silent void. It is a richly structured state, filled with quantum fluctuations arising from the uncertainty principle. If space is divided into two regions separated by a boundary, the vacuum state of the field cannot be written simply as the vacuum of region A multiplied by the vacuum of region B. In other words, Even when no particles exist in the ordinary sense, the vacuum is not a blank background that can be separated piece by piece. At that deeper level, entanglement is already present as a property of the field structure itself, not something that waits to appear only when individual entities collide with one another. What is truly shocking at the level of quantum field theory is this: even when there are no particles in the ordinary sense, the vacuum still does not split into independent parts when we divide space into different regions. The global vacuum state remains entangled across the boundaries between regions. This is not a poetic image meant to make the vacuum sound less empty. It follows from the mathematical structure of quantum fields and has been studied with great rigor in algebraic quantum field theory. One of the deepest results here is the Schlieder theorem. Its technical statement is quite strong, but the intuition behind it can be expressed like this. If one is allowed to act only with local operators inside a non-trivial region of spacetime on the vacuum state, then, in principle, one can still approximate any state in the Hilbert space to arbitrary accuracy. The conceptual significance of this is enormous. It tells us that the vacuum is not an empty, quiet background chopped into separate pieces. It is a state with an extremely deep level of entanglement between regions, so deep that the richness of the whole is already imprinted into the local structure. Of course, this does not open any path to superluminal signaling. Observables associated with space-like separated regions still commute, and that property continues to protect relativistic causality. No local measurement here can be used to send information instantaneously elsewhere. The Schlieder theorem is not about communication. It is about the depth of the entanglement structure already built into the vacuum. Another manifestation of this appears when we change not only the state of the field, but also the motion of the observer. The Unruh effect, predicted by William Unruh in 1976, tells us that a uniformly accelerating observer does not perceive the vacuum in the same way as an inertial observer. For the accelerating observer, what seems like empty space instead appears as a thermal bath of particles. In other words, what one observer calls vacuum, another experiences as having a temperature. This effect is not something we can easily notice in daily life, because the acceleration required to produce even a tiny temperature is already enormous. But theoretically, it follows directly from the way quantum fields are entangled across spacetime regions. If one considers only the portion of spacetime accessible to the accelerating observer, the reduced state they see takes the form of a thermal state. That apparent heat arises because some of the degrees of freedom lie beyond the observer's horizon and have been traced out. This idea echoes powerfully in black hole physics. In 1974, Hawking showed that black holes are not completely black, but emit thermal radiation because of quantum effects near the event horizon. Hawking radiation can likewise be understood as a consequence of entanglement between modes inside and outside the horizon. In this way, entanglement in quantum field theory is no longer just a feature of cleverly prepared laboratory experiments. It reaches all the way into the vacuum, acceleration horizons, and the physics of black holes. Even in the familiar world of high-energy particle physics, this is not exotic. At CERN, in collisions at the Large Hadron Collider, entanglement appears very naturally in scattering and decay processes. Conservation laws such as conservation of total spin or momentum often force the products of an interaction to carry specific correlations, and that means their states are entangled from the very structure of the process. But more importantly, even before any collision occurs, the fields filling space are already entangled across regions. At this point, the perspective shifts yet again. Entanglement no longer appears as a rare effect produced only through delicate preparation. It becomes the natural state of quantum fields. In algebraic quantum field theory, the tension between two aspects of the world becomes especially clear. On the one hand, local observables remain local in the relativistic sense. On the other hand, global states can still be very strongly entangled. These two facts do not contradict each other. They coexist within a subtle but consistent structure. If we divide space into two halves, we can picture this rather clearly. No particles need to be present at all. Yet the quantum field on one side still cannot be described independently of the field on the other. The global vacuum state already contains correlations linking them together, and this is not merely of philosophical interest. It leads to quantities that can be calculated and to real physical consequences, among them entanglement, entropy. In condensed matter physics, entanglement entropy is used to measure how strongly two regions of a quantum system are entangled with one another. In quantum field theory, one particularly striking result is that this entropy often grows in proportion to the area of the boundary between regions, rather than to their volume. This area law behavior has become a profound clue linking entanglement with gravity and the holographic principle. The message therefore becomes increasingly clear. Entanglement is not some optional accessory that can be stripped away from quantum theory while leaving the core untouched. It is woven into the very fabric of the fields themselves. It exists even in what appears to be empty space. It respects relativistic causality, yet at the same time it forces us to abandon the classical idea that distant regions are always fundamentally independent. Particles may come and go, fields may fluctuate, observers may be inertial or accelerating, but the deep structure underneath remains an entangled one. Once that is accepted, the notion of connection becomes far deeper than the image of two particles communicating across a distance. The relations between regions of space are not imposed from the outside. They grow out of the architecture of quantum field theory itself. What once seemed like a strange feature of specially prepared particle pairs turns out, at this level, to be a pervasive quality of the quantum world. From here, the story naturally leads to entropy. Originally, entropy emerged as a way of talking about heat and disorder. In the 19th century, Boltzmann connected thermodynamics to the microscopic world through a powerful idea. Entropy reflects the number of microscopic arrangements compatible with the same macroscopic state. The famous formula engraved on his tomb in Vienna, expressed in words, says that entropy equals Boltzmann's constant times the natural logarithm of the number of microstates. If many different microscopic configurations correspond to the same temperature and pressure, entropy is high. If only a few configurations fit, entropy is low. In classical statistical mechanics, this is almost the same as a measure of ignorance. A gas in a box contains countless molecules, each with its own position and velocity. No one can track all of them. So we describe the system using macroscopic quantities such as temperature or pressure. In that picture, entropy measures how many different microscopic arrangements could produce the same macroscopic situation we observe. Quantum mechanics does not abandon that idea, but rewrites it in a new language. Von Neumann extended the concept of entropy to quantum systems using the density matrix. Instead of counting classical microstates, he defined entropy through an expression that can be read in words as minus the trace of the density matrix multiplied by the natural logarithm of the density matrix itself. Abstract as that sounds, its spirit is very close to Boltzmann's. If a system is in a pure state, described by a single state vector and retaining full coherence, its von Neumann entropy is zero. If it is in a mixed state, meaning a mixture of several possibilities, the entropy is greater than zero. The real power of this language appears when we consider a subsystem inside a larger entangled system. The full composite system may still be in a pure state, with von Neumann entropy equal to zero. But if we look only at one part of it and trace out the rest, the reduced state we obtain is often mixed, with non-zero entropy. When that entropy appears solely because we have ignored the rest of an entangled system, we call it entanglement entropy. The intuition here is beautifully clear in the example of two qubits in a maximally entangled state. Together, the pair is in a pure state. But if we look at only one qubit, it appears completely random, as if the two possible outcomes occur with equal probability. The entropy of the single qubit is then maximal, and that randomness is not due to some hidden variable we have failed to uncover. It comes from the fact that the information about that qubit is no longer contained entirely within itself. it is shared with the other qubit through entanglement. Entanglement entropy, therefore, becomes a way of measuring how information is distributed across subsystems. It is a beautiful bridge between Boltzmann's idea of entropy and the entanglement structure of quantum mechanics. On the classical side, entropy is tied to the number of microscopic arrangements. On the quantum side, entropy also reveals how one part of the world can become mixed simply because it carries within it the imprint of the rest. In classical thermodynamics, an increase in entropy is often understood as a sign that microscopic details are becoming harder and harder to track. Quantum mechanics preserves that spirit, but changes the mechanism. Here, what causes the entropy of a subsystem to rise is not simply disorder, but the stretching out of correlations through entanglement. When a system interacts with its environment, information about it does not disappear. It is dispersed into correlations with other degrees of freedom. And if we look only at that system by itself, its state becomes more mixed, and its entropy increases. That is another way of telling the story of decoherence. As a system becomes increasingly entangled with its environment, the entanglement entropy between them grows. The system's reduced density matrix no longer describes a pure state. The interference terms gradually fade, and from the local point of view, the familiar classical-looking probabilities begin to emerge. In this sense, entropy is not merely a measure of messiness. It is a measure of how far quantum correlations have spread. What matters is that entanglement does not destroy information in any simple sense. It redistributes it. When two systems become entangled, information about each part is no longer contained entirely within that part, but is stored in the correlations between them. The global state of the full system may still remain coherent, but if we examine only one fragment, that fragment will appear more uncertain. This shift from information residing in each part to information residing in the relations between parts is the key. In many body physics, this idea becomes an extraordinarily useful tool. One no longer asks only whether a system is entangled or not, but also measures how entanglement entropy grows with the size of the system. In the study of quantum phase transitions, this becomes an especially powerful signal. In many one-dimensional systems with short-range interactions, the ground state does not cause entanglement entropy to grow with the volume of the region under consideration, but rather with the boundary separating that region from the rest. This is what is known as an area law. From a classical point of view, this is rather strange. Classical correlations tend to grow with the amount of matter or the number of constituents inside a region, that is, with volume. But quantum entanglement is often tied more closely to the boundary. The same pattern appears not only in condensed matter physics but also in quantum field theory. When space is divided into two parts, the entanglement entropy of the vacuum also often grows with the area of the surface separating them. That fact alone already suggests that there is a deeper thread connecting entanglement and geometry than one might first expect. Before moving on to geometry, it is worth pausing at the information theoretic viewpoint. In Shannon's classical information theory, entropy measures the average uncertainty of a random variable. Put into words, it is minus the sum of probabilities multiplied by the natural logarithm of those probabilities. Von Neumann carried this idea into the quantum world. When the density matrix is diagonal in some basis, the von Neumann entropy reduces exactly to the Shannon entropy of the corresponding probability distribution. In that way, entanglement entropy can be understood as the amount of information about one subsystem that has been encoded non-locally into its correlations with the other subsystem. That perspective fits naturally with modern quantum information science, where entanglement is not just a phenomenon to admire, but a resource to use. Protocols such as quantum teleportation, superdense coding, and certain forms of computational speedup all rely on the fact that information can be distributed across subsystems in ways classical physics cannot imitate. In quantum teleportation, for example, what is transferred is neither matter nor energy in any instantaneous sense. What is transferred is quantum information. and the protocol succeeds only if shared entanglement is already in place, together with an accompanying classical communication channel. Entanglement entropy, therefore, becomes a remarkably elegant quantity. It speaks both to foundational physics and to practical information processing protocols. But its power does not stop there. It also opens a path into black hole physics. When Bekenstein and Hawking discovered that black hole entropy scales with the area of the event horizon rather than the volume of the hidden region, that behavior resonated strikingly with the behavior of entanglement entropy in quantum field theory. That resonance led many to suspect that entropy and geometry might be linked far more deeply than classical thermodynamics had ever suggested. At this point, a larger pattern begins to emerge. Entanglement does not merely challenge locality and separability. It also lies beneath decoherence, beneath the classical appearance of the world, beneath new forms of entropy, and beneath the way information is distributed in quantum systems. The classical picture of independent parts, each holding its own information, is gradually being replaced by a web of correlations spread across quantum states. Entropy, once the language of steam engines and gases in containers, has become the language of quantum connection between regions of space and between subsystems of a field. And it is precisely where entanglement entropy reveals its area-scaling behavior, touching horizons and boundaries, that a bold possibility begins to emerge. Perhaps the geometry of space-time is not something that stands prior to entanglement, but is instead deeply related to those very patterns of entanglement. Perhaps distance, curvature, even the structure of space-time itself, are not absolute foundations, but emerge from the organization of quantum information. This runs strongly against classical intuition. In classical physics, geometry comes first. Space is the pre-existing stage. Matter plays out within it. Even in general relativity, where geometry becomes dynamical and responds to mass and energy, geometry is still a fundamental ingredient. Einstein's field equations simply say that the curvature of spacetime is determined by the distribution of energy and momentum. Geometry may bend in response to matter, but it is still part of the original picture. Over the past few decades, the opposite idea has begun to be taken more seriously. Perhaps geometry is not primary, but emerges from patterns of quantum entanglement. One of the earliest places where this intuition crystallized was the holographic principle. Its inspiration came from black holes. Bekenstein and Hawking realized that black hole entropy does not grow with the volume of the inside, but with the area of the event horizon. More precisely, the entropy is proportional to the area divided by 4 times the square of the Planck length, a tiny length scale of about 1.6 times 10 to the power of negative 35 meters. The appearance of area, rather than volume, in that formula suggested something deeply strange. For ordinary systems, we expect that more space means more degrees of freedom, and therefore entropy should grow with volume. Black holes do not behave that way. They seem to count information by surface area. The holographic principle takes that clue as central. It suggests that the informational content of a region of space may be encoded on the boundary of that region, much as a hologram can carry 3-dimensional information on a 2-dimensional surface. If that is true, then the most fundamental description of a volume of space may not reside in the volume itself, but on the lower dimensional boundary surrounding it. And in 1997, Juan Maldacena provided a remarkably powerful realization of that intuition with the ADS-CFT correspondence. In its most famous form, a theory of quantum gravity in a higher dimensional anti-de Sitter spacetime is understood to be mathematically equivalent to a conformal field theory without gravity living on its lower dimensional boundary. Put more intuitively, a world with gravity and an extra spatial dimension can be fully described by a quantum field theory without gravity living on its boundary. This is not a metaphorical comparison. It is a highly non-trivial mathematical duality, supported by an enormous range of calculations. And what is especially striking here is that the extra spatial dimension of the gravitational theory no longer appears as something inserted from the start like a pre-built stage. it begins to look like something that could emerge from the structure of the field theory on the boundary. At that point, the possibility that geometry itself arises from entanglement ceases to be a vague philosophical intuition and becomes a serious direction in modern physics. If the previous sections merely hinted that entanglement might somehow relate to geometry, the Ryu-Takayanagi formula is where that intuition first takes on a clear mathematical form. In 2006, Shinsei Ryu and Tadashi Takayanagi proposed a striking formula. The entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk gravitational spacetime divided by 4 times the gravitational constant. The statement is compact, but its implications are profound. A quantity belonging to quantum information suddenly becomes directly linked to the area of a geometric object. Within the framework of ADS, CFT correspondence, this can be visualized as follows. Choose a region on the boundary and compute its entanglement entropy in the conformal field theory. Then, look into the bulk anti-de Sitter space. There exists a surface stretching inward from the boundary, anchored precisely along the edge of the chosen region. The area of that surface encodes the entanglement entropy. In other words, the bulk geometry appears to record the entanglement structure of the boundary theory. From this point, a bold idea becomes difficult to ignore. Perhaps the connectivity and curvature of spacetime are not primitive facts, but reflections of how different regions of the boundary theory are entangled. If the degree of entanglement changes, the geometry changes as well. In certain scenarios, reducing entanglement between 2 boundary regions causes the bulk spacetime connecting them to narrow or even disconnect. The phrase spacetime is woven from entanglement, therefore begins to carry real mathematical meaning rather than remaining a poetic metaphor. A parallel line of insight comes from many-body physics. In tensor network models, the quantum state of a many-particle system is written as a network of interconnected tensors. The pattern of connections is not merely a computational convenience, it reflects how entanglement is distributed across different length scales. Guifre Vidal introduced the multiscale entanglement renormalization, ANSATS, mirror, as an efficient description for quantum states with multiscale entanglement structures, particularly near critical points. Remarkably, the geometry of networks such as mirror closely resembles the geometry of ADS space. The layers of the network form a hierarchy, each layer carrying information at a different scale. This structure strongly echoes the radial direction in anti-de Sitter spacetime. The resemblance is not merely aesthetic. It reinforces the idea that an extra geometric dimension might emerge from the way entanglement and information are organized in a quantum state. If that is true, geometry is no longer a pre-existing stage. It may instead be the macroscopic manifestation of quantum correlations. From this perspective, even the concept of distance begins to shift meaning. In classical physics, distance is given beforehand. The separation between 2 points is a geometric fact. But if geometry emerges from entanglement, then near and far may reflect the strength of correlations between subsystems. 2 regions that are strongly entangled might appear close in the emergent geometry, while weakly correlated regions could appear far apart. Leonard Susskind once described entanglement as the glue that holds spacetime together. The phrase is metaphorical, but a powerful one. It does not claim that every mechanism is already understood. On the contrary, the detailed dynamics remain under investigation. Yet the mathematical links emerging between entanglement, entropy, holographic duality, and geometric structure are too strong to dismiss as coincidence. Of course, caution is still necessary. These ideas are most rigorously developed in very specific theoretical settings, especially ADS spacetime. The universe we observe appears to have a positive cosmological constant rather than the negative curvature characteristic of ADS geometry. Extending holographic intuition to realistic cosmology remains an open problem. Even so, the conceptual shift is already clear. Entanglement is no longer seen merely as a property of certain particle pairs or elegant laboratory experiments. It is increasingly viewed as something that may lie beneath the structure of spacetime itself. From the holographic principle, through ADS, CFT, to the Ryu-Takayanagi formula and tensor network models, a single theme keeps reappearing. Geometry and entanglement are deeply intertwined. The classical picture of spacetime as a fixed backdrop is replaced by a far more relational view, in which distance and curvature may simply be the large-scale expression of a deeper quantum state. If that is the case, then the question, why do distant things remain connected, may not yet reach the deepest layer of the problem. Perhaps distance itself is not fundamental at all. These ideas remain at the frontier of theoretical physics. They are mathematically sophisticated, conceptually bold, and not yet confirmed by direct experiment in the context of quantum gravity. Yet they represent a serious effort to accomplish one of the unfinished goals of modern physics, unifying quantum theory with gravitational geometry. In that light, entanglement is not merely a strange feature of particles or spins. It may be the scaffolding from which spacetime itself is built. And at precisely this point, the history of physics reveals a curious coincidence. In 1935, two ideas entered science almost simultaneously yet seemed entirely unrelated. One was the famous paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, highlighting the puzzle of quantum entanglement. The other was the Einstein-Rosen solution in general relativity, describing what later became known as an Einstein-Rosen bridge, a kind of wormhole. At the time, no one suspected a connection. One idea concerned quantum correlations, the other concerned space-time geometry. Yet in 2013, Juan Maldacena and Leonard Susskind proposed a bold conjecture summarized in 4 characters: ER equals EPR. The slogan suggests that Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement may be two different descriptions of the same underlying structure. To appreciate the proposal, recall what an Einstein-Rosen bridge actually is. Certain solutions of Einstein's field equations describing black holes can be mathematically extended to reveal a structure resembling a tunnel connecting two distant regions of spacetime. This object is commonly called a wormhole. The simplest version is non-traversable. It connects two regions geometrically, but no object or signal can actually pass through. The throat collapses too quickly, and extreme gravitational effects prevent crossing. The key point is that an Einstein-Rosen bridge represents a topological connection in spacetime. Two regions that appear extremely distant in ordinary geometry may nonetheless be connected through a deeper structure in the bulk spacetime. The ER equals EPR conjecture proposes that certain entangled quantum states may be equivalent, in a precise theoretical sense, to exactly this kind of geometric connection. In the ADS CFT framework, Maldacena and Susskind considered pairs of black holes prepared in a maximally entangled state. Such a pair can be described as two black holes connected by a non-traversable wormhole. The entanglement between the two systems corresponds to the geometric bridge in the bulk spacetime. This does not mean that every pair of entangled particles in a laboratory is literally connected by a tiny tunnel in space. The conjecture does not claim that. Instead, it proposes a deeper equivalence between quantum entanglement and geometric connectivity. ER stands for Einstein, Rosen bridge. EPR stands for Einstein-Podolsky-Rosen entanglement. The conjecture remains theoretical. It rests on the mathematical framework of holographic duality, particularly in ADS spacetime, and it has not yet been directly verified in our observable universe. But it is far from idle speculation. It is supported by the deep mathematical relationships uncovered through AD-CFT since the late 1990s. And here the story of entanglement reaches a new level of meaning. It is no longer only about correlated measurement outcomes. It may also be a clue that the geometry and connectivity of spacetime itself are written, at the deepest level, in the language of entanglement. If the Ryu-Takayanagi formula merely shows that entanglement entropy has a geometric shadow, then ER equals EPR pushes the idea one step further. Perhaps entanglement itself is a form of spacetime connectivity. But here, we must proceed carefully. This does not mean that entanglement allows us to travel through wormholes faster than light. The Einstein-Rosen bridges appearing in these models are non-traversable. No signal can pass through them. Causality remains intact, nor should we imagine that laboratory entanglement experiments have seen microscopic wormholes. The ER equals EPR conjecture operates at the level of theoretical description within specific models of quantum gravity. What it truly suggests is this: instead of picturing entangled systems as distant objects mysteriously correlated across empty space, we might understand them as connected through a deeper topological structure in the fundamental description of spacetime. Seen from that perspective, distance and connectivity are no longer primitive geometric facts. They may be emergent features arising from patterns of entanglement. In that picture, topology becomes central. Two regions that appear extremely distant in ordinary coordinates might still be connected within a higher dimensional description. Conversely, if the entanglement between two regions decreases, the bulk spacetime connecting them could narrow or even separate entirely. Such ideas remain speculative, but they are not arbitrary speculation. They arise from rigorous mathematical structures in string theory and holography. For that reason, increasing effort has been devoted to testing how far ER equals EPR might extend beyond the idealized ad settings where it first appeared. At the same time, thought experiments involving black holes and the information paradox have continued to place entanglement at the center of the story. For instance, in the Hayden-Preskill thought experiment, the question is asked, under certain assumptions about entanglement structure, how quickly could information falling into a black hole be reconstructed from the emitted Hawking radiation? Here, entanglement is not an accessory, it is the ingredient that allows quantum gravity to remain consistent with the principle of unitarity. Even so, the boundaries must remain clear. ER equals EPR is not a hypothesis verified by experiment in the same way as the violation of Bell inequalities. It belongs to an ongoing theoretical effort to reconcile quantum mechanics with general relativity. Its strength lies not in direct data, but in the convergence of many mathematical pieces, from holographic duality to minimal surfaces and entanglement, entropy, all pointing toward a deep connection between geometry and quantum correlations. If that connection is real, then what we once called non-local correlations may deserve to be reinterpreted. Perhaps they do not represent mysterious influences traveling across empty space, but instead reflect a hidden form of connectivity embedded in the deeper structure of spacetime. In that case, the phrase distant objects itself becomes less straightforward than classical geometry suggests. Two systems may be distant within familiar coordinates, yet connected within a more fundamental description. No shortcuts for signals appear. No wormholes allow information to outrun light. The no signaling theorem remains untouched. What changes is the emphasis. The story is no longer about something traveling from one place to another, but about the deeper structure within which both places already reside. In this picture, the universe begins to resemble not an archipelago of isolated objects floating in empty space, but a network of correlations, with geometry reflecting that network. Whether this vision fully captures the nature of spacetime remains an open question. But one thing seems increasingly certain: entanglement has moved from the margins of quantum mechanics to the center of efforts to understand gravity and geometry. And when that shift occurs, the meaning of connection changes completely, not a signal racing across space, but a fundamental relation embedded in the architecture of reality. A similar conceptual shift occurred in another part of physics toward the end of the 20th century. For much of the century before that, quantum mechanics was read primarily as a theory about atoms, particles, and fields. Its strange features were seen as constraints on microscopic behavior, but researchers gradually began to view it differently, not only as a description of nature, but also as a language for processing information. From that insight, quantum information theory was born. One early and influential milestone was the BB84 protocol, introduced in 1984 by Charles H. Bennett and Gilles Brassard. Their idea was both simple and profound. If information is encoded into quantum states, and if measurement inevitably disturbs those states, then two communicating parties can detect the presence of an eavesdropper. Security in this case does not depend primarily on the difficulty of solving mathematical problems. It relies on the laws of physics themselves. Features once considered troublesome, such as superposition and measurement disturbance, suddenly become resources. The basic unit of quantum information is the qubit. A classical bit can be either 0 or 1 at a given moment. A qubit is different. It can exist in a superposition of both possibilities. Mathematically, it is a vector in a two-dimensional Hilbert space, a linear combination of 0 and 1 with complex amplitudes. When measured in a given basis, the probabilities of obtaining 0 or 1 are determined by the Born rule, the squared magnitudes of those amplitudes. Yet the true power of qubits does not fully appear when they stand alone. It emerges when many qubits are combined. Two classical bits can represent one of 4 configurations at a time. Two qubits can exist in a superposition of all 4 possibilities simultaneously, and more importantly, they can be entangled. Entanglement produces correlations that classical systems cannot efficiently simulate. Protocols such as quantum teleportation and superdense coding rely directly on this feature. In superdense coding, for example, two parties can transmit 2 classical bits by sending only a single qubit, provided they already share an entangled pair. Once entanglement is treated as a resource, the question of quantification becomes unavoidable. How much entanglement does a given state contain? Can it be strengthened or weakened? Can it be converted from one form into another? For pairs of qubits, William K. Wouters provided a quantitative answer in the late 1990s through a quantity known as concurrence. This number ranges from 0 to 1. 0 corresponds to a separable state, while 1 represents maximal entanglement. Although the formula itself is somewhat technical, its meaning is straightforward. It measures how deeply 2 qubits are bound together. This quantification is crucial because entanglement behaves differently from classical correlations. Using only local operations and a small amount of classical communication, one cannot transform a weakly entangled state into a more strongly entangled one without additional resources. But there is a subtler route: entanglement, distillation. If two parties share many copies of weakly entangled states, they can sometimes extract a smaller number of states with stronger entanglement through coordinated local operations and classical communication. This procedure makes it clear that entanglement behaves like a genuine resource, something that can be consumed, concentrated, diluted, or deployed in communication tasks. From this point, the entire discussion fits naturally into the framework of resource theory. In that framework, we distinguish between operations that are considered free and resources that carry genuine value. For entanglement theory, local operations and classical communication are typically regarded as free. The valuable resource is entanglement itself, because it enables tasks beyond the reach of classical models. And once again, entanglement appears not merely as a strange feature of nature, but as something that can be measured, managed, consumed, and harnessed as a real physical resource. Once entanglement is viewed as a resource, the question is no longer simply, is it strange? But rather, what does it enable that ordinary operations cannot? It is precisely here that the rigorous frameworks of resource theory become important. Many researchers, including Fernando Brandão, have helped clarify something that sounds simple, yet is deeply foundational. If we restrict ourselves to local operations and classical communication, which transformations of quantum states are actually possible? And how should measures of entanglement behave under those restrictions? One central principle in this picture is monotonicity. If a quantity is to be called a measure of entanglement, it must not increase under local operations plus classical communication. Otherwise, we would have accidentally allowed entanglement to be generated for free, and the entire notion of a resource would collapse. This principle is what makes entanglement resemble a constrained kind of power. To obtain more of it, One must pay with genuine quantum structure, not merely with local tricks. And when we place this in the setting of communication, its value becomes very clear. Quantum teleportation, proposed by Bennett and collaborators in 1993, is an almost perfect example. There, the state of a qubit can be transferred from one place to another, provided the two parties already share an entangled pair and also exchange two classical bits to complete the protocol. What matters is that the original state does not remain intact after the process. It is destroyed, exactly in the spirit of the no-cloning theorem. An unknown quantum state cannot be copied perfectly. What is transferred is neither matter nor an extra duplicate, but the quantum state itself, reconstructed elsewhere. In computation, the role of entanglement also appears as an extremely powerful ingredient, though subtle debates remain about whether it is absolutely necessary for every form of quantum advantage. What seems fairly certain is that powerful quantum computations usually rely on highly structured, entangled states. Experimental platforms such as superconducting qubits and trapped ions are trying to generate and preserve entanglement not merely among a few qubits, but across dozens or even hundreds of them. Yet this is also where the practical paradox of quantum mechanics becomes obvious. Entanglement is both the strength and the vulnerability. It enables computation beyond classical limits, but the moment unwanted entanglement with the environment appears, the useful entanglement inside the computational register is rapidly degraded by decoherence. Quantum information theory therefore changes the tone of the entire discussion. In the past, people asked what entanglement meant philosophically. Now they also ask what it can do in practice. That does not erase the foundational questions, but it forces them to become more grounded. Entanglement is no longer a conceptual ghost. It is something that can be measured, manipulated, quantified, and assigned real value in the informational sense. That transformation reflects a familiar theme in physics more broadly. Many ideas first appear as abstract paradoxes, but once they are understood with sufficient precision, they become tools. Entanglement was once invoked as evidence of incompleteness, or as a sign of the strangeness of the quantum world. Now it stands behind secure communication systems and the effort to build quantum computers. In that picture, information is no longer merely a metaphor. It is a genuinely physical quantity, constrained by quantum laws. Entanglement determines where information resides across subsystems, how it spreads, how it can be concentrated, and what tasks it can be used to accomplish. Perhaps one of the most beautiful examples of this shift is quantum key distribution. When entanglement first entered physics, it seemed little more than a philosophical inconvenience. But in 1991, Arthur Eckert showed that it could do something very concrete: help create secure communication. In his protocol, two parties share many pairs of maximally entangled qubits. Each side measures its qubit along randomly chosen directions. Because the particles are entangled, the outcomes they obtain are correlated in a way that violates Bell inequalities. The elegance lies in the fact that these correlations accomplish two things at once. On one hand, they generate a shared random key that the two parties can later use to encrypt information. On the other hand, they serve as an intrinsic security test. If an eavesdropper intervenes, their measurement or interception will disturb the fragile entanglement between the particles. In that case, the observed Bell violation will no longer match what is expected, and that discrepancy itself becomes the warning signal. Security therefore no longer depends mainly on whether an adversary has enough computational power to break a code. It depends on the fact that nature does not permit intervention without leaving traces. This is no longer just a beautiful idea on paper. Quantum key distribution systems have been implemented in laboratories and have even entered a limited number of commercial networks. The greatest obstacle has always been distance, because photons traveling through optical fiber are gradually absorbed and scattered. After tens or hundreds of kilometers, preserving the signal becomes difficult. To overcome that limit, researchers have had to bring entanglement into space. With the Messier satellite, Jian Wei Pan and collaborators distributed entangled photon pairs between ground stations separated by more than 1,000 kilometers. In experiments like these, Earth itself becomes part of the apparatus, and entanglement is no longer confined to the laboratory. But communication is only half the story. Computation is the other half. In 1994, Peter Shaw published an algorithm that startled both the cryptography community and computer science more broadly. The problem of factoring large integers had long resisted efficient classical solution. The best-known classical methods still grow very rapidly with input size. Shaw's algorithm showed that a quantum computer could, in principle, perform the task in polynomial time. The impact of this result was not merely theoretical, because cryptographic systems such as RSA depend heavily on the practical difficulty of factoring sufficiently large integers. At the heart of Shaw's algorithm is the use of superposition and interference to perform the quantum Fourier transform efficiently. But for the whole machine to function as intended, different parts of the computational register must be bound together in ways that classical structure cannot reproduce. It is precisely here that entanglement enters as the internal connective tissue of the computation. If the global state decomposed only into independent parts, full quantum advantage would not arise. Grover's algorithm, introduced 2 years later in 1996, tells a different story. It does not provide exponential speedup like Shaw's algorithm, but rather a quadratic speedup for the problem of unstructured search. On a classical computer, to find one marked item among items, one typically needs about 2 queries on average. Grover reduces that to roughly the square root of 1, a pontivit. For very large databases, that difference is still enormously significant. The algorithm works by repeatedly amplifying amplitudes, concentrating probability onto the desired solution. And during that process, entanglement often appears as part of the structure binding the qubits together. Of course, the precise role of entanglement in quantum speedup is not a completely settled matter. There are settings in which states are highly mixed and the amount of entanglement is not large, yet some quantum advantage still appears. In other cases, strong multipartite entanglement seems indispensable. But one thing is very clear. Classical correlations are not sufficient to reproduce the full range of what quantum algorithms are doing. The state space of many qubits grows exponentially because the tensor product structure of Hilbert space forces it to do so. With only 50 qubits, the dimension of the state space is already 2 to the power of 50, a number larger than 1 quadrillion. And it is within that enormous space that entanglement becomes the structure that organizes, binds, and pushes quantum possibilities far beyond what any classical model can keep up with. If we look at materials through classical intuition, we usually imagine that their properties are simply the cumulative result of local interactions among constituents that are already independent. But quantum condensed matter physics forces us to change that perspective. There, what determines a phase of matter, or the behavior of the whole system, is no longer the individual particles taken one by one, but the collective wave function of many particles at once, a wave function often so deeply entangled that it cannot be separated into independent parts. Once again, the old theme returns in a new form. Not independence, but correlation, is what shapes reality. Materials that appear stable and completely classical on large scales still rest on a quantum microscopic foundation. There are phases in which entanglement is present only as a hidden layer, difficult to detect directly. But there are also phases in which entanglement becomes the decisive feature. Superconductors are like that. Topological materials are as well. Quantum Hall systems too. In such cases, the connection between distant parts of the material is not just a poetic way of speaking. It is literally encoded in the many-body wave function of the entire system. So the story of entanglement no longer stops at 2 photons or 2 qubits. It becomes the invisible architecture underlying whole phases of bulk matter. The same principle that once produced striking correlations in Bell tests is now what binds electrons into superconducting pairs and organizes topological states in quantum Hall systems. From the smallest scales to the macroscopic properties of materials, entanglement remains present as part of the fabric of physics. But the farther we go, the more clearly another fact comes into view. Even though the links between entanglement, information, and geometry have become increasingly dense, physics still does not possess a complete theory of quantum gravity. The outline of the problem is very clear. Quantum mechanics works extraordinarily well at very small scales. General relativity successfully describes the very massive and the structure of space-time itself. Both have been experimentally confirmed within their own domains. Yet their mathematical frameworks are so deeply different that combining them into a single unified whole remains one of the great problems of modern physics. Quantum mechanics speaks in the language of Hilbert space, linear operators, and probability amplitudes. General relativity speaks instead in the language of a smooth space-time manifold, whose curvature responds to energy and momentum. On one side, quantum theory. On the other, geometry. One side is built from probabilities and operators, the other from fields and manifolds. That foundational difference has kept theorists busy for decades. One major path is loop quantum gravity. Beginning in the 1980s, Abhay Ashtekar and many collaborators reformulated general relativity using new variables now called Ashtekar variables that make the gravitational field look closer to a gauge theory. In this picture, space-time geometry is no longer a smooth, continuous fabric. It is quantized. Area and volume operators do not yield continuous spectra, but discrete values. Space is described by spin networks graphs, whose edges and nodes carry quantum numbers, and those networks serve as the quantum states of geometry. The idea here is powerful. Perhaps geometry cannot be divided forever. At extremely small scales, around the Planck length of about 6 × 10, 35 meters, space may no longer be a continuous background, but instead be made of discrete quanta of geometry. Within that framework, entanglement once again does not disappear. It appears as relational information between the nodes of the spin network. The connectivity of the graph determines geometric relations. Space, in this sense, begins to look like something arising from algebra and combinatorics, rather than from a pre-existing smooth geometric backdrop. Loop quantum gravity is a serious framework and remains actively studied. It has achieved some partial successes, such as reproducing black hole entropy consistent with the Bekenstein-Hawking area law under certain assumptions. But it still has not produced experimental signatures sharp enough to distinguish it decisively from competing approaches. Another route is causal set theory, developed by Raphael Sorkin and collaborators. This approach starts from a very different point. It assumes that space-time at the fundamental level is not a continuous manifold, but a set of discrete events ordered by causal relations. In that picture, the number of elements carries information about space-time volume, while the order structure encodes who can influence whom. Geometry and curvature, if they emerge at all, must arise statistically from the distribution of those discrete elements. What makes causal set theory attractive is that it preserves the central role of causality from general relativity while introducing discreteness at the deepest level. It does not assume a geometric background in advance, but attempts to build space-time out of elementary events. Yet, like loop quantum gravity, it remains a developing program. Conceptual clarity is one thing. Connecting it to familiar low-energy physics and extracting sufficiently sharp experimental signatures is another. Alongside these direct quantization programs are broader ideas in which spacetime is not regarded as fundamental from the start. Inspired by holography and entanglement entropy, some researchers suspect that spacetime is only a large-scale approximation, emerging from deeper degrees of freedom, perhaps patterns of entanglement, or more abstract informational structures. In that picture, connectivity comes from patterns of correlation, and geometry reflects the way information flows. This is precisely the spirit already visible in ADS, CFT, and tensor network models. But extending those intuitions from idealized ADS models to our actual expanding universe, with its small positive cosmological constant, remains an open problem. All of these approaches run into the same experimental barrier. Quantum gravitational effects are expected to become clear at the Planck scale, where energies are around 10 to the power of 19 GeV. By contrast, the Large Hadron Collider at CERN reaches about 10 to the power of 4 GeV. The gap between those scales is 15 orders of magnitude. That number alone is enough to show why directly probing Planck-scale physics with present-day accelerators is impossible. For that reason, if there is hope, it often lies in indirect signatures, tiny deviations in the propagation of ultra-high-energy cosmic rays, distortions in black hole evaporation, or distant imprints in the cosmic microwave background. But so far, there is no truly unambiguous evidence, widely accepted by the broader community, for quantum gravity. The difficulty is not only experimental. Even at the conceptual level, the tensions remain deep. One of the most famous is the problem of time. In canonical approaches such as loop quantum gravity, the Wheeler-DeWitt equation describing the quantum state of the whole universe contains no explicit time parameter. That makes the question painfully sharp. If the fundamental formalism appears timeless, where does the experience of evolution and the flow of time, the thing we live with every day, actually come from? Another tension is the black hole information paradox. If a black hole evaporates completely through Hawking radiation, what happens to the information about the matter that fell into it? Quantum mechanics, with its unitarity, requires that information be preserved, yet the original semi-classical calculations seem to imply information loss. More recent developments from holographic intuition to page curves have leaned toward the possibility that information is in fact preserved in extremely subtle correlations within Hawking radiation. Even so, a full consensus has not yet emerged. There is another challenge as well, embedded in the very spirit of general relativity: background independence. In relativity, space-time geometry is dynamical. There is no fixed stage standing outside the drama. But many quantum field theories are built on pre-assigned geometric backgrounds. A truly satisfactory theory of quantum gravity, if it follows that ideal, should avoid assuming a rigid background from the outset. Each current framework captures part of the story, but leaves another part exposed. So the picture today is not that of a finished theory, but of a living landscape of exploration. Loop quantum gravity quantizes geometry directly. Causal set theory discretizes space-time events. Holographic approaches suggest that space-time emerges from entanglement. String theory, though not explored in depth here, brings extra dimensions and extended objects to center stage. Taken together, they point towards something very clear. Entanglement is no longer just a strange detail of quantum mechanics. It is increasingly becoming a clue for understanding not only particles, fields, or matter, but space-time itself, the arena in which everything unfolds. If we look at materials through classical intuition, we often think that their properties simply arise from local interactions among individual components. Each particle seems to act independently, and large-scale phenomena appear to be nothing more than the sum of those small behaviors. But quantum condensed matter physics reveals a very different picture. In many quantum systems, the phase of a material and the way it behaves are not determined by each particle separately, but by the collective wave function of countless particles all at once. This wave function often contains such a deep degree of entanglement that the system cannot be separated into independent parts. This shift in perspective recalls an idea that has appeared many times throughout the story of quantum theory. Independence is not the foundation. Correlations are what shape reality. Materials that appear completely classical and stable at large scales are in fact supported by quantum interactions at the microscopic level. In some phases, entanglement exists in a very subtle and difficult to detect way. But in other phases, it becomes the most important feature. Superconductors can carry electric current without resistance because electrons pair up in an entangled state. Topological materials display robust properties because they are organized by patterns of entanglement spread across the entire system. In quantum Hall systems, the precise plateaus of conductivity arise from collective correlations among many electrons. In this context, the connection between distant parts of a material is not merely a metaphorical image. It is written directly into the many-body wave function of the whole system. As a result, the scope of the story begins to widen. Entanglement is not just a bridge between two photons or two qubits in delicate experiments. It is also the invisible architecture beneath phases of matter. The same principle that produced strange correlations in Bell tests is also the principle that binds electrons into superconducting pairs and organizes topological states in quantum Hall systems. From the smallest scales of physics to the properties of bulk materials, entanglement remains present as part of the structure of reality. Even so, despite all the progress in linking entanglement with information and geometry, physics still does not possess a complete theory of quantum gravity. The problem can be described quite clearly. Quantum mechanics governs the very small. General relativity governs the very large and the very structure of space-time. Both theories have been experimentally confirmed within their domains of validity, but their mathematical frameworks are profoundly different. Quantum mechanics is built on Hilbert spaces, linear operators, and probability amplitudes. General relativity, by contrast, describes spacetime as a smooth geometric structure whose curvature responds to energy and momentum. Reconciling these two descriptions into a single unified theory has been a goal of theoretical physics for many decades. One important approach is loop quantum gravity, developed in part by Abhay Ashtekar and collaborators beginning in the 1980s. In this approach, general relativity is rewritten using new variables, often called Ashtekar variables. These variables allow the gravitational field to be described in a way that resembles gauge theories. Within this framework, the geometry of spacetime is no longer a perfectly smooth continuum. Instead, it becomes quantized. Quantities such as area and volume do not take on all continuous values, but instead come in discrete ones. Space is described by spin networks, graphs made of nodes and edges carrying quantum numbers. These networks represent quantum states of geometry itself. The basic idea is that geometry cannot be divided infinitely. At extremely small scales, around the Planck length, space may be made of discrete quanta. In this picture, entanglement still plays an important role. The states of spin networks encode relations among the nodes of the graph. The way the nodes are connected determines geometric relations. From this point of view, geometry does not arise from a pre-existing smooth spacetime background. It emerges from combinatorial and algebraic mathematical structures. Loop quantum gravity is a mathematically consistent framework and remains an active area of research. Under certain conditions, it can reproduce black hole entropy in a way consistent with the Bekenstein-Hawking area law. However, so far, it has not produced clear experimental predictions that would decisively distinguish it from other approaches. Another direction is causal set theory, developed by Raphael Sorkin and collaborators. This theory begins from a different assumption. It proposes that spacetime is fundamentally discrete, and that its basic structure is a set of events ordered by causal relations. In this view, spacetime is not a continuous manifold, but a collection of discrete elements. The number of elements reflects spacetime volume, while the order relations among them encode causal structure. Geometry, including curvature, would then emerge statistically from the distribution of these elements. Causal set theory preserves the central role of causality from general relativity while at the same time introducing discreteness at the most fundamental level. It does not assume a pre-existing geometric background, but instead constructs spacetime from elementary events. Like loop quantum gravity, this approach is still under development. It offers conceptual clarity regarding discreteness and causality, but connecting it to familiar low-energy physics and identifying concrete experimental signatures remains a major challenge. Some other hypotheses take an even broader direction. Inspired by holography and entanglement entropy, some researchers suggest that spacetime may not be fundamental at all. Instead, It may emerge from patterns of quantum entanglement or from deeper informational structures. In these viewpoints, patterns of entanglement determine how different regions of a system are linked, while geometry reflects the flow of information. These ideas are closely related to earlier discussions of the correspondence between ADS spacetime and conformal field theory, as well as tensor network models. However, extending these intuitions beyond idealized models to our actual expanding universe, where there exists a small positive cosmological constant, remains an unresolved problem. All of these approaches face the same major experimental difficulty. Quantum gravitational effects are expected to become important at the Planck scale, where energies are around 10 to the power of 19 electron volts. By comparison, the Large Hadron Collider at CERN currently reaches energies of about 10 to the power of 4 electron volts. The gap between these two energy scales spans 15 orders of magnitude. For that reason, directly probing Planck-scale physics with present-day particle accelerators is beyond current technological capability. Some researchers look for indirect signatures, such as tiny deviations in the propagation of high-energy cosmic rays, changes in the evaporation process of black holes, or subtle traces in the cosmic microwave background. So far, however, there is still no clear experimental evidence confirming any specific theory of quantum gravity. In addition, deep conceptual tensions remain. One example is the problem of time. In canonical approaches such as loop quantum gravity, the Wheeler-DeWitt equation describing the quantum state of the universe contains no explicit time parameter. This raises the question of how the time evolution we observe could emerge from a description that appears to be timeless. Another tension is the black hole information paradox. If a black hole evaporates completely through Hawking radiation, what happens to the information about the matter that formed it? Quantum mechanics requires information to be preserved, but the original semi-classical calculations suggested that information might be lost. More recent developments, including holographic ideas and calculations involving the Page curve, suggest that information may be preserved in subtle correlations within Hawking radiation. Even so, full consensus on this issue has not yet been reached. Another challenge concerns background independence. In general relativity, space-time geometry is dynamical. By contrast, many quantum field theories are built on fixed geometric backgrounds. A truly complete theory of quantum gravity, ideally, should not assume a fixed space-time stage from the outset. So the current picture remains an open field of research. Loop quantum gravity attempts to quantize geometry directly. Causal set theory constructs space-time from discrete events. Holographic approaches suggest that space-time may emerge from entanglement, and string theory introduces extra-spatial dimensions and extended objects into the fundamental description of nature. So far, no single approach has achieved complete experimental confirmation. This is not a failure of physics. Rather, it reflects the extraordinary difficulty of trying to unify two of the most successful theories ever constructed. Quantum mechanics and general relativity have both been tested with extremely high precision within their respective domains. But bringing these two pictures together forces physicists to work at scales of size and energy far removed from ordinary experience. In many current efforts, entanglement continues to play a central role, whether in holographic dualities, spin networks, or calculations of entanglement entropy. Quantum correlations repeatedly appear alongside geometry. The conceptual tensions that remain unresolved show that the story is not finished. The connections between information, space-time, and gravity are compelling, but they are not yet fully understood. What is certain is that entanglement is not a rare phenomenon confined to laboratory experiments. It penetrates the structure of matter, the emergence of the classical world, and possibly even the structure of space-time itself. The final answers about quantum gravity remain beyond present observation. Yet the questions themselves continue to sharpen our understanding of how systems separated by large distances can remain related at the deepest level of physical law. After all the equations, experiments, interpretations, and hypotheses linking distant regions of spacetime, the question returns in its simplest form. Two systems are separated. The distance between them may span kilometers. Light requires a finite time to travel from one system to the other. Yet when measurements are performed, correlations appear in a way that no local classical model can reproduce. The answer is not that a secret signal travels through space faster than light. The no-signaling theorem guarantees that no controllable information can move faster than light. The theory of special relativity, established in 1905 and confirmed through particle physics experiments and satellite navigation systems, remains entirely valid. The answer lies in structure. Entangled systems share a single quantum state. That state is described within a Hilbert space constructed from the tensor product of the subsystems. If the state cannot be separated into independent parts, then the systems are no longer independent in the classical sense. Even if they are far apart in space, their connection remains encoded in the structure of the shared state. Consider a pair of particles prepared in a spin singlet state. The total spin of the system is well defined, but the spin of each particle individually is not. The state encodes relational information. When one particle is measured, we learn something about the other, because both are described by the same inseparable quantum state. Nothing is transmitted at the moment of measurement. The correlation was already encoded when the state was prepared. In 1964, John Bell demonstrated that no theory based on local hidden variables can reproduce the correlations predicted by quantum mechanics. Bell inequalities place quantitative limits on classical models. Experiments by Alain Aspect in the early 1980s, followed by increasingly refined tests by Anton Zeilinger, Ronald Hansen, and many other research groups have repeatedly observed violations of those classical limits. The measured values approach the quantum limit of about 2.828, consistent with quantum predictions while never exceeding them. Data collected over decades from laboratories around the world and even from satellite experiments have led to a stable conclusion: entanglement is real. The structural viewpoint explains why this does not conflict with relativity. The reduced density matrix describing one subsystem does not change when the measurement choice on the other side changes. Local statistics remain unaffected. Correlations only become visible when the results from both sides are compared through ordinary communication channels. Entanglement, therefore, reflects shared structure rather than signal exchange. From an informational perspective, entanglement spreads information across subsystems. The entropy of one subsystem increases when it becomes entangled with another. Information about the entire system no longer resides in each part individually, but in the correlations between them. In quantum information theory, entanglement becomes a resource. It enables quantum key distribution, quantum teleportation, and computational advantages. The degree of entanglement can be measured through quantities such as concurrence. It can be distilled and manipulated using local operations combined with classical communication. From this viewpoint, distant systems remain related because they participate in a shared informational structure. The classical idea that each system carries a complete set of its own properties is replaced by a relational description. The geometric perspective extends this idea further. In quantum field theory, even the vacuum state is entangled across spatial regions. The Rieschleider theorem shows that local operations can approximate global states because the vacuum already contains strong correlations. In holographic dualities, the entanglement entropy of a region in a boundary theory corresponds to the area of a geometric surface in a higher dimensional spacetime. The Ryu-Takayanagi formula connects entropy with area. The conjecture ER equals EPR suggests that entanglement may correspond to geometric connectivity such as Einstein-Rosen bridges. These ideas do not mean that particles in a laboratory are literally connected by traversable tunnels. Rather, they suggest that connections in quantum states may admit geometric interpretations at deeper levels of description. Across the structural perspective, the informational perspective, and the geometric perspective, a common theme appears. Classical separability is not fundamental. In classical mechanics, The state of a composite system is simply the collection of the states of its parts. In quantum mechanics, the state of the whole system may contain correlations that cannot be reduced to individual components. Independence is therefore only an approximation. Decoherence explains why classical independence appears in everyday life. When a system becomes entangled with its environment, interference between different macroscopic states is suppressed. Stable states emerge, and information is redundantly recorded in the environment. At large scales, objects behave as though they possess definite individual properties. That behavior is real and reliable, but it is an emergent phenomenon rather than the deepest level of description. The concern raised by Albert Einstein was not simply about faster-than-light signals. It concerned the assumption that distant systems must possess independent real states. Quantum mechanics modifies that assumption without abandoning experimental discipline. Its predictions are extraordinarily precise. The correlations are measurable. The limits are defined. The mathematical structure is consistent. So why can distant systems remain connected? Because at the quantum level, distance does not guarantee independence. Systems that once interacted may share a common state even after they have moved far apart. The connection is encoded in that shared state. The world is not made of completely separate pieces linked only by local forces. It is organized by patterns of correlation that sometimes extend beyond classical boundaries. This does not break causality. It does not allow arbitrary influence to cross space. It simply changes how we understand separation. The classical picture of distinct objects with intrinsic properties remains extremely useful in everyday life. It emerges from decoherence and environmental entanglement. But beneath that layer lies a deeper relational structure in which relationships appear before individual properties. Entanglement is not an anomaly. It is a window into that deeper structure. Distant things remain related because, in some states, they were never completely separate to begin with. This conclusion is supported by decades of experiment and mathematically consistent theory. It suggests a shift in perspective. Perhaps connection is not something that travels through space. Perhaps space itself reflects those connections. Quantum entanglement tells us something precise and fundamental about the laws of physics. The state of a composite system cannot always be reduced to the states of its parts. Non-separability is written directly into the mathematical structure of quantum mechanics through the tensor product structure of Hilbert space and the existence of states that cannot be factorized. This phenomenon has been tested repeatedly from Bell's theorem in 1964 to the experiments of Alain Aspect and the increasingly refined tests of Anton Zeilinger, Ronald Hansen, and many other groups. The experimental conclusion has remained consistent. Nature violates classical inequalities. Quantum predictions are confirmed within experimental uncertainty. No faster-than-light signaling occurs. Relativistic causality remains intact. Theory, experiment, and information structure all agree. Quantum mechanics predicts entanglement. Experiments confirm it. Quantum information theory measures and exploits it. Quantum field theory shows that it exists even in the vacuum. Holographic dualities suggest that it may even be related to geometry. Across all these domains, the same principle repeats. The whole can possess structure that cannot be fully described by listing its individual parts. At the same time, caution remains necessary. Not every speculative extension has been confirmed. Proposals in quantum gravity remain active areas of research. They are strongly motivated mathematically, but direct tests at Planck energies remain beyond current technology. What is no longer in doubt is the core phenomenon. Entanglement has been measured, created in laboratories, and harnessed in technology. It secures communication. It shapes materials. It produces correlations that classical theories cannot reproduce. Classical separability, which feels so natural in everyday life, arises from decoherence and environmental interaction. It is an effective description rather than the deepest layer of nature. Beneath that layer lies a relational structure in which systems can share a common state across space without any signal traveling at the moment of measurement. Distance still matters. Causality still holds. But independence is conditional. Entanglement does not make the world more mysterious. It makes the picture more precise. It shows that connection can be structural rather than dynamical. In that sense, distant systems remain related because nature allows states that transcend classical separations. The result is not a paradox but a deeper consistency. Distance and connection coexist within a single framework. And that framework, built from experiment and mathematics, continues to guide the search for a more complete understanding of physical reality.